All right. So yeah, thanks for inviting me. So I want to talk about generalization theory. If I could make my slides progress, there we go. So I'm going to focus on probabilistic formulations of prediction problems and the generalization questions that arise in those. And one of the key tools there is uniform laws of large numbers. So we'll spend a fair chunk of time on that question, on some of the tools that we have for attacking that. We'll go a little bit more deeply into some Radamaca averages stuff and skate over a bunch of other techniques. And in the second half, we'll look at some of the implications for neural networks. And then we'll look at some more recent questions that have come up. I mean, it's a bit of a change of flavor for the last part, looking at this phenomenon of benign overfitting and some of the results that have been seen in that area. So there's a bit of variety. Just in terms of interrupting for questions, I can't see the chat. I don't think. I mean, I've hidden the window that has the chat. So if you do have questions, you're welcome to speak up. If that becomes cumbersome, we can adjust things, and I can pull that window up and block my slides that way. But let's try it like that. And I can open it up and check the chat every so often. But do feel free to interrupt and ask questions. I'd prefer that to people not understanding things and missing chunks of the rest of the presentation. Okay, so let's get started. The first thing we'll look at is how we might formulate some of these prediction problems. So the kind of stereotypical case to think about is a classification problem, but more generally, we can think about predicting some sort of outcome. We'll always have our outcomes be Y from a set, a capital Y, of possible outcomes. And we're doing that on the basis of some pattern X that comes from a set capital X. The idea is we have some training data to help us with this task. It's a sequence of XY pairs. There are N of them. We'll write those as X1, Y1 through Xn, Yn. And we want to use those to choose some function that maps from the space X to the space Y, so that on subsequent XY pairs, we make good predictions. Our F of an X gives us a good prediction of that Y. And to formalize that, we do it in a decision theoretic sort of setting, where we talk about the utility of a prediction, or the loss of a prediction. So we define some sort of loss function that maps from pairs of these outcomes to the reals. Typically, that's going to be a bounded range. We usually think of these losses as being positive. And the loss of a prediction Y hat in the face of an outcome Y is just that cost of making that prediction. And we aim for that loss to be small when we're using this. We want to choose a function F so that for an XY pair, F evaluated at X gives us a prediction that incurs small loss for the outcome Y. There's a very broad class of problems that you can set up in this sort of a way. This is a nice general approach to a whole lot of decision problems. One of the things I'm going to narrow us down to here is thinking about IID data, but just to give a couple of examples, that do fit that assumption. In pattern classification, we're thinking of classifying a pattern into one of some finite number of classes, one of the simplest losses is the 0-1 loss, where we just incur a loss of 1 if we make a mistake on our prediction Y hat, and a loss of 0 otherwise. We might, of course, we might have different kinds of mistakes incurring different kinds of losses. We might be concerned with the flavor of many different kinds of flavors of pattern classification problems, I guess. Let's leave it at that. In a regression setting, when the outcome space is the reals, you know, we would typically choose some sort of a continuous loss, like the quadratic loss, which is a squared difference between our predictions and the outcomes. And the key assumption we're going to make here, we set things up in a probabilistic setting. So there's some probability distribution on this product space X times Y. And we see training data X1, Y1 through Xn, Yn. I'm using capital letters to denote random variables. And there's, you know, another XY pair. All of these things are chosen independently according to this probability distribution P. And we're aiming to have the expected loss that we incur with our predictions be nice and small. So this, we call this the risk. We're using the symbol capital L for the for a function f that's making predictions. We use the symbol capital L of f to denote the expectation of the loss incurred on a random XY pair. And, you know, our aim is to have that as small as possible. Okay, and so in pattern classification for the 0-1 loss that I defined earlier, that's just the misclassification probability. The expectation of this indicator of making a mistake is the probability that we get things wrong. Okay, so let me see if I can check out. All right, good. So as I say, do feel free to interrupt if there are any questions. All right. So we're thinking of this distribution P as modeling the relative frequency of different kinds of patterns that we see in the world, and also the relative frequency of the labels that an expert would assign to that pattern, or the distribution, conditional distribution over these outcomes Y, given the pattern X. You know, it's a very strong assumption that we're seeing IID data. We'll be making that assumption. We'll be also making assumptions about things like tails of X's, tails of the losses that are incurred. You know, these are the sorts of assumptions that we need to make for the sort of results that we're gonna see. You know, certainly we need some sort of stationarity. We need something about the training data that's in common about our goal of having the expectation of the loss of F on X with outcome Y being small. Only about having that somehow related to our training data. Okay, and you know, of course, this is a very natural way to do it. Now, I'll be sort of heavy-handed on this slide with what's random and what's not, and then we're going to sweep it under the rug. So, you know, it is good to keep this in mind. At least sweep it under the rug in terms of our notation. So, you know, but I want to be quite clear on this slide. So our sample X1, Y1 through Xn, Yn is random. You know, this is generated from the same probability distribution. And when we look at the function on a subsequent input X, we should really be thinking of that as a random function, because it depends on the training data. For brevity, I'll write that training data as dn. And so, you know, when we write L of Fn, I mean, the subscript n here, you know, is used throughout to denote things that depend on the sample of size n. So when we write down the risk L of Fn, I told you that was the expectation. It's actually, you know, the conditional expectation. In this case, where Fn is random, we're actually going to use that to denote the conditional expectation of the loss that it incurs on a random XY pair, conditioned on the training data. So that is a random variable, right? It depends on that random sequence of X1, Y1 through Xn, Yn that we've seen. And you know, we might aim to have the expectation of that loss of that random variable small, that risk. Or we might aim to have it small with high probability. The probability we're talking about here is the randomness that goes into Fn, and that's that training sample. Okay, and of course, you know, the key difficulty here is we don't know the probability distribution. We only get to learn about it through the random data, X1, Y1 through Xn, Yn. Okay, and what we're going to be considering is, you know, we're really focused on formulating questions in this probabilistic way that are relevant to large-scale machine learning methods. So, one way to view those is that they somehow choose a function fn from some fixed class of functions. We'll use script f to denote that. Maybe these are linear functions over a Euclidean space. Maybe they're sparse linear functions. They're linear functions where the coefficient vector has a small number of non-zero entries. Maybe they're all the functions that a ReLU network with some particular architecture can compute, as its parameters range over all of their possible values. Maybe they're functions that are ReLU network with a fixed depth and unbounded width, but some sort of constraint on the scale of the parameters throughout the network. There are all sorts of ways you can formulate these classes of functions. We're gonna look at it abstractly as there's this class f, and what are the features of f that are important. So yes, I guess that's one of the questions, right? We're interested in designing algorithms for which our choice fn is close to the best that we could hope for, given that we're restricting ourselves to making choices from this class capital F of functions. So what that means is we want to get close to the best that we could have hoped for within that class, right? So we have this minimal risk over our class F of functions, and we want to compete with that. We want our fn to have risk that's almost minimal. We're interested in how that depends on the sample size, on things like the complexity of the class of functions, on properties of the probability distribution, for instance, also. Sometimes we're more ambitious. We might think about this class of functions, about a very rich class of functions. We might aim to compete with all measurable maps from our input space to our output space. So we're hoping to have, as the sample size grows, to have our risk approaching the best possible, the minimum over all measurable functions of the risk of it. In order to do that, we need to be a little more careful about how we work with this class of functions. We typically work with a complexity hierarchy. So a sort of range of richness or complexity to the different functions that we use. So these are the kinds of questions that we might hope to answer. Okay. And just to distinguish this approach from some of the sort of classical parametric statistical results and ideas that you will encounter in mathematical statistics, we're really in a more non-parametric world. We're concerned with results that are applying to large classes of probability distributions. And typically we're not making parametric assumptions about the process that generates the data, right? So, I'm not so interested in making the assumption that the particular class of functions I'm using is a great model for the world. If it is, then I'm happy with that, and working with that class is certainly going to be advantageous. But we're typically not making these parametric assumptions that there's some, let's say, finite dimensional parameter and like family of Gaussians or something, and our probability distribution comes from that family. So at least for most of these talks that I'll be giving. And we're focused instead on working with this class of this fixed class F and competing with the best performance from that class, with only mild assumptions on the actual process generating the data, and therefore how good that best performance might be. And just one comment here. When we do this, look at analyzing the performance of statistical methods of algorithms that produce these functions Fn, it's typically easier if that function is some sort of explicit if we can write Fn as an explicit function of the training data. That's the case, for instance, for linear regression. I've written it down here when we've got a data matrix X and a vector of outcomes Y, and we're interested in a least squares, ordinary least squares estimate. we can write down explicitly in terms of that data, what this function is going to look like for any subsequent x. And that makes the analysis a lot simpler, and we'll see examples of that later on. But often we have to work with somehow implicit properties, right? So for instance, our Fn might be a solution to some optimization problem. Logistic regression is an example of that. Or it might be the outcome of some iterative procedure, like AdaBoost, where we're progressively using the data to progressively improve the performance on our training sample. So in these cases we get things that are implicitly depend on the training data, and we can use properties of that dependence, but we in some sense need to work a little harder. Okay.
There's a question on the chat.
Great.
It says, can you explain the equation in point 1 on slide 11?
Slide 11. Great. Thanks, Dash. So let's see what the equation in point 1 on slide 11. Yeah. Okay. So this term, L of Fn minus the infimum of L of F. I guess that's what Dash is asking. Yeah. So we're saying here, we'd like to use the training data to choose some function Fn from the class capital F. The best we could possibly hope for, and our aim is to have the risk, the expected loss of that function, small. The best we could possibly hope for is the minimum over all functions in our class F. I've written it as the infimum here. I guess the minimum may not be achieved. The infimum over all functions in our class F of the risk. This is the best case scenario. And if we knew the probability distribution, in principle, we could identify the F that minimize this or get as close as we like to it. But we only have the training data, and we'd like to get our risk as close as possible to that ideal, given that we're restricted to choosing functions from the class F. All right, so this having this quantity go to 0, for instance, as the sample size grows, is a very natural goal. Yes, so infimum is the best lower bound, right? We want to get the risk as small as possible. It might not be a minimum, so there may not be a function that actually achieves that optimal risk. But if it's only something that if it's an infimum but not a minimum, then we can get arbitrarily close to it, but possibly not actually achieve it. Yes, so capital F is a class of functions. Sorry, who wrote that? CJ. A capital F is a class of functions, and there are a bunch of examples up here, right? It could be something parametric like linear functions, or a ReLU network with some fixed number of parameters, or it could be something non-parametric like a ReLU network with constraints on the size of the parameters, but not on the number of parameters, or some more abstract function space like classical smoothness classes, Sobolev spaces, and things of that sort, if you're familiar with those. Okay. If there are no other questions, let's move on. Oh, one more. Good. Let's see. Okay, so let's talk about uniform laws of large numbers. So this is really an approach to answering questions of the flavor that was on that previous slide in this probabilistic setting, and we'll see how it arises. So okay, let's think about there's a family of methods, of prediction methods that work by optimizing a sample average as an estimate of as a replacement for the risk. So we can replace the risk, which is the expectation of this loss function, by a sample average of that risk. So an expectation under the empirical distribution, the distribution the average over the training data that we see. So we write this empirical risk as L hat. So for a function f, L hat is defined as the average over the training sample, the x1, y1 through xn, yn, of the loss incurred on those points. This is quite natural. If you think about a pattern classification problem, you might try to find a function in your class that classifies the largest proportion of points correctly. Or in a regression problem, we might try to find a function that incurs the smallest squared error on the sample that you've seen. Okay, and I'm introducing this notation here, P sub n of L. It's sort of operator notation. Think of that as something like an expectation of the loss, but I want to be explicit about what distribution I'm computing the expectation with. In this case, the expectation is under the empirical distribution, which I'll denote by P sub n. That's the distribution that puts mass 1 over n at each of the xi, yi pairs. Okay, so I'm going to use this notation throughout this section, and it's a little unusual, but it makes a lot of the arguments actually pretty clear. It makes, I think the notation is strange, but it's worth it. So good to get your head around that. Okay, so we talked about I've written here F star. So I wrote an infimum earlier, and now I'm saying arg min, as if that infimum was a minimum. This is, assuming that it exists, this is the function in the class that achieves the smallest risk. If it doesn't exist, replace this argument with something where F star is as close as you like to the infimum, let's say within some epsilon, and you can make that epsilon as small as you like. So okay, let's think about the best or some almost optimal function in our class, and that first question we wrote was, how far is the risk of the function that we choose based on the training sample? Let's say using empirical risk minimization, how far is that from the optimum? Okay, so very simple argument here is to write the risk of that empirical risk minimizer minus the risk of the optimum. So this is the excess risk, how much above the best we could hope for we are. To write that as just a sum of different pieces, right? I'm subtracting, I take the risk of Fn, I subtract off the empirical risk, so how well it did on the sample, and add it back in. I subtract off the empirical risk of the optimal function, F star, and add it back in, and then I'm looking at, minus the risk of F star. I've just rewritten this thing, but split it into 3 pieces. Okay, and 2 of these pieces are really very easy to deal with. The easiest one, I guess, is this one when I'm talking about empirical risk minimization, because Fn is the minimizer of the empirical risk. And so in particular, it does at least as well as F star. So this quantity is always no bigger than 0. All right, now let's think about the other 2 terms. Right, the third term here, it's the difference between a sample average, right, the average on the training data, and an expectation of the loss that this optimal function F star incurs, right? So that's a fixed function from XY pairs to reals. And, the difference between the sample average and the loss, and I'm gonna get you accustomed to this notation, right? I'm writing Pn minus P as the expectation under the empirical distribution, that's the sample average of this random variable, minus P is the expectation under the population distribution, the true distribution that generates the data. Okay, so I'm interested in that last term is looking at how the sample average of the loss for F star exceeds, how much the sample average exceeds the expectation. Okay, well, that's just a fixed function. So this thing is just a fixed random variable. So we're really just asking a question here of, how close is an average to an expectation? There's, we know from the law of large numbers that term's going to go to 0. And actually, if we have a little more information about it, besides just, so we're going to have information about the tails of the loss, for instance. Or more generally, things like a sub-Gaussian property. Information about the tails, such as boundedness of the loss, or more generally, something we call a sub-Gaussian property. We'll meet that a little later on. briefly, then you can be quite quantitative about how the sample average exceeds the expectation, how rapidly those two get close to each other. So this term's sort of easy to deal with. As I said, this second term is always non-positive because we're considering the empirical risk minimizer. And then that first term, that's more problematic, right? This is the expected risk, the risk, I'm sorry, of the empirical risk minimizer minus the empirical risk. Now, we can't just appeal to a law of large numbers here, right? Because we don't have a single random variable that we're considering. Our Fn depends on the data. So, this is a random variable, the Fn. And we should expect this to be biased because we're choosing the function because it looked good on the data, right? If we pick a single function like f star, then it's this empirical risk is an unbiased estimate of the risk. But when we choose Fn from some class to minimize the empirical risk, we get a biased estimate of this risk, the expected loss. I say not necessarily zero in expectation, unless you're in a totally trivial situation where you can only choose effectively one function. The expectation, it is a biased estimate. It certainly doesn't have expectation zero. Okay, so how do we deal with that? So here I'm going to write down a very simple inequality. It seems really very, very loose, and we'll have something to say about that looseness a little later. But an easy upper bound on this deviation between the expected loss, the risk of Fn, and the empirical loss is the supremum over the class of the difference between these expectations and sample averages. Okay, so no matter what emerges as the empirical risk minimizer, it's certainly got that difference is certainly upper bounded by the maximum over the class of these two. Of the difference between these two. Okay, and having this quantity on the right-hand side go to zero is stronger than just a law of large numbers. A law of large numbers is telling us that for any fixed f, we've got a random variable there whose sample average is converging to its expectation. This is what we need here is a uniform law of large numbers. We need that uniformly across the class, these sample averages are approaching expectations, that the maximal over the class, deviation between sample averages and expectations, is something that's getting small as we see more data. Okay, so that's an inequality. Certainly it gives us a sufficient condition for empirical risk minimization to work. Gives us a way to handle many other approaches besides empirical risk minimization. I mean, if you look at what's going on here, for any method Fn, we can estimate its performance in terms of its empirical performance plus this sort of notion of deviations between expectations and sample averages. So that gives us information about the sample complexity of a learning problem. We get upper bounds on how much data we need in order to achieve a particular performance. It also leads to insight into algorithm design. The kind of complexity, you can view these terms as complexity penalties, right? If you write this inequality as the risk of the function that my method produces is upper bounded by the empirical risk plus this term, that term's kind of a complexity penalty that gets added to the empirical risk. And so, you might consider optimizing a regularized version. You take the empirical risk and you regularize it with something that depends on the complexity of the class of functions. And so if we have a hierarchy of functions, so in particular, if we can understand how this notion depends on some natural notions of complexity of our class of functions, then that's a natural candidate for a complexity penalty in a regularization sort of approach of that kind. Okay, I see we've got a few more questions in the chat, so let's take a look at those. Right, so LFN versus LF star versus L hat FN versus L hat F star, right. Okay, and Wisson's answered that. Yeah, so that's right. So we're always thinking about these functions as being from the class F, at least at this moment in the talk. The point is that we're yeah, so there are a few different things floating around here. Let me go back to the slide. Okay, so when we're talking about the last term, so L hat is, as Wison said, this is the sample average. So measuring loss on the training data, whereas we're interested in the expectation of the loss, I guess for the function Fn, right? We're interested in the risk for Fn. This is how Fn looks on the training data. This is how F star looks on the training data. And this is how F star, how good F star really is. This is its risk. It's the expectation of the loss. And when we split things up in this way, you know, we've got this is a comparison of the empirical risk for Fn, and in our case, when we're minimizing empirical risk, you know, we're choosing Fn so that this is the smallest it can be across the class F. F star is another function from the class F, so it's in particular not going to be as good as Fn on the training sample. It certainly can be better than Fn in terms of the expected loss, but on the training sample, we chose Fn to be the best. Okay, so I think that was your last question, Dash. And you know, the point I'm making about uniform laws of large numbers versus just laws of large numbers, if we have a single function and we're interested in, we fix a function and then we say, okay, I'm going to go and evaluate it on some training data. This is how good its expected loss is. And now I see a sample, a random sample for that function. You know, this has expectation given by the risk. It's just an average of random variables that have this distribution. And as we average more and more of those random variables, we get a better and better approximation of the expectation. Right, so going back to the definitions here, where did we write the loss? Was the expectation, right? L of F is the expected loss, right, under a random XY pair. L hat of F is the empirical loss, so the sample average over the training sample. Right, so hats here are denoting, you know, it denotes something that depends on the sample. It's the empirical proxy for the expectation of the loss. Okay, great. So we got up to this point and we were talking about uniform laws of large numbers. And, you know, okay, so we're going to get one step more abstract now. So here I'm talking about the expectation of the loss incurred by a function f when we look at predicting with f. So it's the loss of f of x when the outcome is y. And this L hat is the sample average of the loss incurred by the function f on the sample, you know, the xy pairs. Okay, so we're going to talk about function classes over a more abstract space. We'll write our function classes G on a set Z. For our learning application, that set Z is the product space, right? It's XY pairs. And the function class G is the composition of losses with functions from our class. So, you know, we've been thinking about this random variable. So for an XY pair, you incur a loss with the function when you use f to predict outcome. Your prediction is f of x. The outcome is y. You incur loss L of f of x and y. And we're thinking about these as the real valued functions that we're considering. So they map from XY pairs to the losses incurred for a fixed function. And we've got a class of functions because we can make all sorts of different choices about the prediction rule F that we use. Okay, so I'm going to switch from writing losses everywhere to just thinking about functions G, and I've incorporated the loss into the function. Okay, just because we're going to be arguing about quantities like this, the supremum over a class of functions of the difference between an expectation and a sample average. Okay, we're going to be discussing those things, and I want to kind of lose the loss notation. So we'll do that by talking about a function class G, and for our learning application, we should think about that as not the functions, the prediction rules themselves, but the losses that they incur on these XY pairs. And our set Z now is slightly richer. It includes the outcomes as well. Okay, and so this point of view is we can draw a cartoon here, right? So this is sort of on the x-axis is the set of all functions that we might be using for prediction. The blue line is supposed to represent the expectation of those functions. I shouldn't have said all functions we use for prediction. All functions on our space Z. And we're always concerned with losses, so we're interested in minimizing these things, but just abstractly, we're thinking of them as functions. The blue line represents the expectation of those functions. And look, there's a point here, which corresponds to the best we can do, the smallest expectation. This is our goal. We want to predict as well as we can. So we want the expected loss for a prediction rule in our class to be minimal. Well, that function, let's call it G star, might be here in this cartoon representation of the space of all functions. That's our goal, but unfortunately we don't have access to this plot of expectations. All we have access to is a sample, right? So we get these Z1 through Zn. In our case, they're XY pairs, and we can evaluate the loss on those XY pairs, and we can look at the average loss as we vary across the different functions. And in this cartoon, I've shown that as a wiggly line. It's supposed to be, for any particular function, it's supposed to be an unbiased estimate, but it might vary quite wildly as we move across all these different functions. And if we drew a different sample, we might get some quite different variation for those empirical estimates, the sample averages. And now if we go ahead and minimize the sample average across this very rich space of all functions on our x-axis, we might end up over here, right? Which is when we look at the function that we choose, its expectation is really way higher than the best we could have hoped for. We've done quite badly because we're working with a class of functions that's very rich. And in particular, these deviations, when we look across this full set of functions, these deviations between sample averages and expectations can be really quite large from at least this cartoon. Okay, but of course, all we see is this picture. We don't know the expectations. We can do much better if instead of looking at all functions, we look at a restricted family of functions that are, much more controlled in their complexity. And we'll kind of fill out this cartoon with some examples a little later. If we look at a restricted family of functions, then we might hope that within that family, the deviations between expectations and these red sample averages is not too big. And so, when we minimize the empirical, the sample average, we can get something whose true performance is not much worse than the best in that family of functions. Okay. We pay a cost for restricting ourselves to a family of functions. Maybe it's linear functions, maybe it's ReLUs of a particular flavor, in that the best in that class might not be as good as the best when we look across all measurable functions. Okay, so so abstractly, the problem that we're interested in is we have a class of functions. We're going to say that they map to 0, 1. So we've got losses in a bounded, our losses have a bounded range. And we've got, IID data, and we're interested in the, there's an X there, that should be a Z. Sorry about that, typo. We're interested in understanding the supremum or maximum over our class G of deviations between expectations and sample averages, right? When we see a sample of size n. Okay, and I'm going to use this notation. We'll go into a bit more detail in a moment about the notation, but I'm going to use this notation that's writing down a norm of an empirical process. The norm here is kind of maximizing an absolute value over a class G, and this empirical process is deviations between expectations and sample averages. So what's an empirical process? It's a random variable that's a function of something. In this case, it's a function of the functions G, right? So you give me a G, and my empirical process P minus Pn gives you back a random variable, right? And that random variable is the difference between the expectation of G and the average on the sample of that G. Okay, so that's an empirical process, and we're interested in some notion of scale of that empirical process. The notion of scale in particular is what's the largest value of the largest absolute value of that random variable when we look across the full class G. Okay, so that's the notation we're going to use, and this is the quantity that we're interested in. Of course, it's a random variable. It depends on this empirical distribution is the distribution that puts mass 1 over n at these points z1 to zn. So it's a random variable. It depends on this randomness. We might hope that as that sample size grows, this random variable converges to 0. And in that case, we say that the class G obeys a uniform law of large numbers, right? We don't just have the usual law of large numbers where sample averages are approaching expectations. We have that happening uniformly across the class, that the worst case across G of those deviations is going to 0. So that's what we mean by uniform law of large numbers. Okay. Having that quantity go to 0 is is our goal here. The usual terminology for this is a Glavenko-Cantelli class. We say that this class of functions is a Glavenko-Cantelli class for a given probability distribution if this maximal deviation between the sample average and the expectation, which in our notation is this G norm of this empirical process, is something that converges to 0, with some notion of stochastic convergence. I've written converges in probability to 0 here, but we'll see that in our case we can say something stronger. Okay, so just to go through, make sure we're on the same page with this notation and what we mean. P here is a distribution on the space Z. So we have our random variables Z1 to Zn that are drawn IID from this probability distribution P. Pn is the empirical distribution, the one that assigns mass 1 over n to each of those points in our sample. We've got this class G of real valued functions on Z. And we're interested in this class. Pn minus P is an empirical process. So as I say, a stochastic process that's indexed by a class of functions G. Think of that as a mapping from a function in G that takes you from a function in G to a random variable. And what we're interested in is somehow the size of that empirical process as measured by this kind of norm. It's the maximum over G of the absolute value of that random variable, right? The thing that is the deviation between sample averages and expectations. Okay, so we're using this sort of notation and terminology. I think it's very, very convenient for the sort of manipulations that we're going to do. Okay, and why is it called Glavenko Cantelli? So there are these two mathematicians, a Russian and an Italian mathematician that I guess at the same time in 1933 came out with a particular example of a uniform law of large numbers. They were interested in deviations between the cumulative distribution function of a random variable and the empirical cumulative distribution function, right? So if you have a random variable like a Gaussian, it's got this nice smooth CDF, and we could gather a sample from that distribution. Maybe we get 100 points, and then we plot the cumulative distribution function, which is, we can write as Fn, right? It's the average of these indicators. At any point X, it's the proportion of points in the sample that are smaller than that, right? And so you would see steps at each of the points in our sample when we plot out this cumulative distribution function. And these guys were interested in how good an approximation that empirical CDF is of the true CDF of a random variable. It turns out that for any distribution, you have a very good approximation. So that the infinity norm, that is the maximum deviation between these two across, as you look across the real line, the infinity norm is something that goes to zero almost surely as the sample size grows. Okay, but you can think of that as actually being equivalent to a uniform law of large numbers, but for the particular class G, that is the class of indicators, right? Of X being less than some value, right? Because we're taking sample, the empirical distribution is looking at the sample average of those indicators, and the true CDF, the empirical CDF, I'm sorry, is the sample average of those indicator functions, and the CDF is the expectation of these things. So it's precisely maximal deviation. This infinity norm here is precisely the maximal deviation across these indicator function, this indicator function family of deviations between expectations and sample averages. Okay, and we're interested in looking more generally than just at these step functions. Okay, first of all, it's clear that not all function classes are Glavenko Cantelli classes. So here's an example of a function class F. Somehow I've lost the calligraphic typesetting that I had. Here's an example of a function class that is does not have this Glavenko Cantelli property. It's just defined on the real numbers. It's the class of indicators for some finite set. So every function in this class is defined in terms of some finite set S, and that function maps to 1 on that set and 0 off the set. Okay, so so that's a class of functions that takes values in 0, 1. But it clearly doesn't have this Glavenko Cantelli property, because think about what expectations look like, right? Let's suppose we have a continuous distribution. So the measure of any finite set is 0. Then the expectation for every function in the class, the expectation is 0. On the other hand, when we look across that class, we can always find a function. So you give me a sample of size n, I can always find a function that's 1 on those points, and 0 for almost all other points. So that function in particular has a sample average of 1, but we know every function in the class has an expectation of 0. So for any particular function, of course, the sample, we're just not going to hit the finite sample, the finite set of points where it's non-zero. And so this sample average of F approaches the expectation, actually with probability 1, as soon as you see a single sample, you're almost always going to be almost surely going to have Pn of S equal to P of F. But if you look uniformly across the class, the maximal deviation between expectations and sample averages is as big as it can be here. It's 1. So that class is too rich to have this Glavenko-Cantelli property. Okay. So, the key tool we're going to use to understand Glavenko-Cantelli classes is something called Radamaca complexity. I wonder if this would be a good point to take a short break. Maybe just like a 5-minute break, so people get a little chance. So how about are there any questions about the idea of uniform laws of large numbers, kind of where we're going with the rest of this section? All right, if not, let's take how about a 5-minute break? So we'll be back on the hour. I shouldn't say that. India has a half-hour time difference. Okay, so we'll be back on the integral half hours, and pick up again with Radamaca complexity. See you soon. All right. So let's get started again. Oh, there's a message in the chat. Right. Why is the Glavenko-Cantelli property useful? Right. So let's just go back again to where we're looking at the motivation here. So when we're interested in understanding how well our prediction rule Fn performs, we're interested in it having small risk. That's the expectation of the loss here. And we can write, we can't, the best we can hope for here is to have the risk close to the best in the class. We saw we could split that up into 3 pieces. 2 of those pieces are very easy to deal with, the second and third. And they're things that we expect to be either non-positive or small as a function of the sample size, going to 0 as the sample size grows. And this first one, is where all the action happens. So in understanding the performance of a prediction rule, in particular, the one that optimizes its loss on the training sample, its average on the training sample, we want to understand this first term. How does the deviation between the expected loss and the average of the loss over the sample behave? And we did that. We looked at this upper bound, the max over the class of prediction rules of those deviations. So this is the quantity that we're working with. Glavenko-Cantelli class is one for which the sort of corresponding maximal deviation between expectation and sample average goes to 0 as the sample size grows. So that's what we'd hope for, right? If we don't have that property, then there are functions in the class for which, then we might be stuck with choosing a function that has a very big deviation, even as the sample size gets larger and larger, seeing more and more data, and we're still in trouble. So that's the motivation for studying these GC classes. And as we get quantitative about these maximal deviation inequalities, we're going to be able to say, for a certain class of functions, this sort of difference between the risk and the empirical risk is something that is bounded by such and such a term in terms of the sample size, in terms of kind of complexity properties of the class of functions that we're working with. Okay, so so that's where we're headed, and the Radamaca complexity, you know, it turns out is a sort of central object in the Glavenko Cantelli property, central object in these uniform laws of large numbers. So we're going to look at you know, a particular proof that we have this GC property. There are two kind of key parts to the proof. One is that the deviations we see between expectations and sample averages, which is a random variable, that this sort of random variable is actually tightly concentrated around its expected value. So all we need to worry about is the expectation of this random variable. And then the other part of the argument is a symmetrization step that says, you know, we can relate this expectation to something called the Radamaca complexity of the function class, and actually related in both directions. So, you know, if you're interested in deviations between expectations and sample averages in these maximal deviations, the Radamaca complexity is in some sense the right quantity. So what is the Radamaca complexity? It's an expectation of a norm of another empirical process. This one is the process that, you know, you give me a function g and I'll give you a random variable, right? So it's indexed by the function class again. And that random variable is the average across the sample of not g evaluated at the zi's, the z1 through zn, but g evaluated at the zi's, and each one of them multiplied by an epsilon I, right? And these epsilon i's are plus minus one independent uniform random variables. They're Radamaca random variables. Okay, so that's sort of a strange beast. Instead of, you know, instead of taking an average of the g's, it's sort of an average of these symmetrized versions of the values of g's. So when we then take the expectation of the biggest absolute value of this thing across the class, what are we doing? We're looking for functions that are, in some sense, you know, when we evaluate them on these zi's, they're sort of aligned with the random plus minus ones. So here's another way of thinking of that. Let's think about the g evaluated at z1 through zn as defining a certain vector, right? So if you give me a z1 through zn, then we can think about the vector g of z1 through g of zn. It's a vector in Rn. And as I vary the function g across this class, I'm getting a set of vectors in Rn. You know, maybe it looks like this shaded area down here. Okay, and you know, pictorially, if the z's lie in the real line and these lines, squiggly lines, are our functions g, then the vector here is, you know, the evaluations at all of these different points. G at z1 is the first component, g at z2 is the second component, and so on all the way to g at zn. And we look at all of those n vectors that we can get as we vary the functions in our class. Okay, so we get a subset of Rn that way. And what we're looking for here is the expectation of the maximal alignment, in the sense of this sort of inner product, maximal alignment between the epsilon vector, right, the plus or minus one vector, which is just a random direction, and you know, this set of n vectors. So, you know, if this line here represents a certain random choice of the epsilon vector, we're looking for the maximal alignment in our set with that vector, right? So it's a measure of sort of the size of our set. If we can have an alignment with lots and lots of different random directions, then we have a very rich set. If this quantity is small, then we don't have such a rich set. Okay, so that's the Radamaca complexity. I have a question. Oh, no, that was a response. That's the Radamaca complexity, and here's a result. You know, I'll step through it. The sort of bottom line here is that the maximal deviations between expectations and sample averages are very closely tied to the Radamaca complexity, right? So first of all, we have that the expectation of those maximal deviations is upper bounded by the Radamaca complexity, or twice the Radamaca complexity. If our class is bounded, which is a convenient assumption, we'll stick with that case. If our class is bounded, for instance, we're talking about losses and our loss function is bounded, then these expected deviations are not just upper bounded by the Radamaca complexity, they're lower bounded by it as well, with a different constant, and minus something that goes to 0 as n gets large. And that's a result about the expectation that says, it's within a constant factor, it is the Radamaca complexity, the expected maximal deviation. If we look at the random variable that is this maximal deviation, right? So it's random, of course, because it depends on the sample size. This thing is something that's tightly concentrated around its expectation. So with probability that goes exponentially fast to 1, it's very close to the expectation. So think of these. We want this thing to be like a nice big constant. Then we should have the thing inside the exponential to be a nice big constant, right? So we have a high probability statement, then we should have these epsilons looking like 1 over square root of n, or constant over square root of n, right? So again, we've got quantities that are going to 0 like 1 over square root of n in these deviations. Okay, so in particular, if we have the Radamaca complexity getting small as the sample size grows, then we have these maximal deviations getting small also. So the Radamaca complexity really is the right quantity. It's if we want this GC property. Okay, so let's talk about why that's true. And I'm going to go into a bit of detail here. This is really the only part of these lectures where I'm going into proofs, and I'm doing it because it really is quite simple and gives you I think some nice intuition about what's going on with these sort of deviation inequalities. There are sort of two key steps here, and they involve this symmetrization idea. It's a very nice idea. If you haven't seen it, it's certainly worth knowing about. So the first step is to say, well, look, we're interested in the difference between an expectation and a sample average. Well, we can rewrite that first expectation as an expectation of a sample average under an independent sample, right? So what I've written here is an expectation, a conditional expectation, where we fix the sample, Z1 through Zn, right? So these guys are just, fixed numbers. And I'm looking at taking the expectation, so integrating out this ghost sample, a new sample I'm just imagining, right? Z1 prime through Zn prime. These have exactly the same distribution. So when I take an expectation of an average of these G of Zi primes, well, that's just the expectation of G for this term. And the second term is the sample average, right? So I've just rewritten the expected maximal deviation between expectation and sample average by rewriting that first expectation here, rewriting the first term, the expectation, as a conditional expectation of the over this new sample. And then, the inequality here is just Jensen's inequality, right? I'm saying that I can if I take the expectation outside, then I'm only going to get something bigger, because here I've got a supremum of an absolute value of something. If I take the expectation, then I'm doing all that maximizing an absolute value business inside the expectation. I get something bigger. Okay. And now, this is an expectation of a conditional expectation. So, well, that's just an expectation, right? I'm just averaging over these things as well. So I get an expectation of this maximal deviations between these maximal deviations between an average over one sample and an average over another sample. Okay. I'm going to write that this way. So, you know, all I've done is replaced the P, that true distribution, by another sample average, Pn prime. Okay. So this quantity is the expectation of the max over our class of the absolute difference between an average on this ghost sample, Z1 prime through Zn prime, versus an average on the original sample, Z1 through Zn. Okay. How did we deduce the lower limit in slide 27? Yeah, we're gonna get to that. The lower limit. I guess maybe I misunderstood. Dash, do you mean how did we deduce the thus statement? Is that, yeah, okay, good. So okay, so this does follow from what's going on here. So if you know, think about the case where P minus Pn, where these maximal deviations are going to zero, then in particular, this quantity is going to zero as n grows, right? This is the limit we're considering here. If that's going to zero as n grows, then you know, this epsilon is sort of a thing that goes to zero as n grows. It's like 1 over square root of n. So we must have that this thing is going to zero as n grows. And for that to go to zero as n grows, we must have, wait, I'm sorry, I said that backwards. If this thing is going to zero as n grows, then, you know, that's certainly going to zero, and we must have this expectation going to zero. And then if that expectation is going to zero, you know, again, that thing's going to zero as n grows, so we must have this thing going to zero as n grows. You know, that's that direction. And conversely, if that guy's going to zero, then this must be going to zero, and that going to zero, together with, we know this term, we can make things with high probability go to zero, right? Then this thing must be going to zero. And you know, I wrote, I've just vaguely said going to zero, you know, to have an almost sure statement, we're using the fact that actually we can integrate out these tail bounds because we have sort of probabilities of this event happening being exponentially close to 1, right? So that's using a Borel-Cantelli lemma for folks who've met that before. Also, what does it mean to symmetrize? Yeah, so we're making things more symmetric here. So we started out with something that was an expectation and a sample average, and we difference between those two, and we turned it into something that was more symmetric, which is a sample average and another sample average, right? So we've got something that's you know, somehow more symmetric than we started with. And actually, the next step is also a symmetrization step in, but here we're symmetrizing the two samples that we have and making them in some sense indistinguishable. So, you know, we had this quantity as our upper bound on the previous slide. And now we're saying, well, look, if you were to introduce a plus minus 1 random variable for each I, for I going from 1 to n, you know, I've written out this term. It's just the expectation of the supremum of the sample average under the prime sample versus the sample average under the original sample. And I'm claiming that that's equal to the same expectation where I put the epsilon I, this plus or minus 1 sequence, doesn't matter what it is, you know, maybe epsilon 1 is plus 1, epsilon 2 is plus 1, epsilon 3 is minus 1, just fix a sequence. Whatever that sequence is, I'm claiming that this expectation, when I change the sign here, is exactly the same as this expectation. Why is that? Because by changing the sign, you know, all I'm doing is kind of swapping what I call Zi and what I call Zi prime, right? But these are all independent, identically distributed random variables. So I may as well have called Zi prime Zi or called it Zi prime. You know, it doesn't matter what I label them. They're identical in their distribution. And that means in particular that when I look at, you know, this random variable, it has the same distribution, and I'm just taking the expectation of that. Okay, so so I haven't changed anything in terms of the expectation when I introduce this this change of sign here. Okay, since that was true for any plus minus one, I could actually choose the epsilon randomly, and it's still true. I still have this this equality, and so I'm going to choose the epsilon i's to be uniformly plus or minus one and independent. Okay, and that means, you know, in some sense, the zi's and zi primes really are indistinguishable. You know, I might put one first or the other, and it doesn't make any difference. Okay, so now we have all the ingredients to understand why the Radamaca complexity comes in. We've got this quantity, which is our, you know, we showed that we've got an upper bound on our expected maximal deviation between expectations and sample averages. We could write it in terms of this ghost sample with an epsilon I in there. So now this is easy to manipulate, right? We can just take a triangle inequality to say, well, this is an average of epsilon I g zi primes minus an average of epsilon I g zi's. And I'm taking an absolute value. Well, I can upper bound that in terms of the sum of those two absolute values. You know, this one plus the average corresponding to this one. And that's what I've written out here. And actually, I upper bounded it by taking a separate supremum on each side. And of course, I'm taking the expectation of these two terms. Okay, but now, you know, look what we've got. These zi primes and zi's, they have the same distribution. We have, you know, the expectation of exactly the same random variable here added together twice. So that's twice the expected supremum of one of these terms, which is exactly the Radamaca complexity. Okay, so this was our definition. So, you know, we've turned things from deviations between expectations and sample averages into alignment of functions with these random plus minus one directions. Okay, and you know, these steps gave us an upper bound here. We can also get a lower bound. That's called a you know, historically has been called a desymmetrization inequality. You can get a lower bound by going through you know, some similar steps. Things are taking a bit longer than I'd planned, so I might skip the steps here, but it's really using just the same sort of ideas, triangle inequality kind of ideas, adding and subtracting some expectations in here, using a triangle inequality, symmetrizing again, replacing that expectation with a symmetrized version, and then adding and subtracting some expectations and using again a triangle inequality in the same way to get, you know, the same way as we did on the previous slide. There's a second term that arises that involves you know, an expectation of G multiplied by, you know, sort of a absolute value of an average of these epsilon i's. Well, that average of the epsilon i's, you know, is something that we know goes to zero, like 1 over square root of n. That's sort of actually follows from some later calculation. We'll see. Okay. So that was the bound in terms of the expectation, the relationship between the expected supremum and the Radamaca complexity. The other part was a concentration part that says that, you know, actually these deviations are always very close, with high probability, very close to their expectation. So, you know, there's a whole lot of work on concentration inequalities. Just to give you a bit of a flavor of that, what we're going to exploit here is that, you know, this random variable is something that's concentrated because it uses, because it has a particular property, something called the bounded differences property, that means that with high probability, it's not too far from its expectation. I wrote this as an upper bound, but there are upper and lower bounds on the deviation between this random quantity and its expectation. Okay, so what's the bounded differences inequality? So first of all, we're thinking of this random variable as some function of the independent Z1 through Zn, right? So you take the Z1 through Zn and compute, this number, right? The max over G of the expectation of G minus the average on those Z1 through Zn. So that's a function. And the crucial property here is that the function doesn't depend too much on any one of those Zi's. Okay, so what does that mean? Well, if we think of that function as taking, its n inputs, and these are going to be the independent random variables. And the crucial property is that if I take those n inputs for any value of them and substitute a new value for one of them, right? So all the ones up to I minus 1 are the same, and the ones from I plus 1 on are the same, and I've changed the ith one, then the value of the function changes by no more than bi, let's say. Okay, that's a bounded differences property if this is true uniformly across all of the possible inputs this function could take. Then it turns out that when you consider the function evaluated on n independent inputs, the deviations between the value of the function and its expectation are going to be small, right? The probability the deviation exceeds t is no more than e to the minus something like t squared over the sum of the bi squares. So if these are big numbers, you have a weak result here. But if they're pretty small, and in our case, they're like 1 over n, right? So we get a sum of 1 over n squareds. There are n of them, so that's a 1 over n. So we get an e to the minus n times t squared here in this term. So that's something that as n grows is, going down to 0 like e to the minus n for any fixed t. So, why in our case do we get the change of just 1 over n? Because our functions g take values in the interval 0, 1. So if we change any one of those zi's, all we can do is have this average change by 1 over n. And, we're taking absolute value, we're maximizing over g, but this is true for every g. So that thing can only change by 1 over n when we change one of the zi's, which gives us this very tight concentration of these deviations. Okay. So this is also called Mcdiamond's inequality. Colin McDiarmid popularized it. It's also known as the Höftinger-Zuma. No, I guess this is a generalization of that. The Höftinger-Zuma is gives essentially the same result under more restricted conditions. To apply the bounded differences inequality, is there any distribution assumption for the xi's such as sub-Gaussian? No, so the crucial assumption here is let me go back to this. Crucial assumption here is I guess we need these to be independent, the x1s through xn's. But it's the sort of tails or scale of the values of the function that's important here. It's not any properties of the independent data that goes into it. So we don't need anything beyond the independence of these guys, but we do need that no matter what those inputs are, if we change one of them arbitrarily, we've got a very limited impact on the change to the function. That's the crucial property that we need there. All right. So that's a key result here that says, if we're interested in these maximal deviations between expectations and sample averages, then that's really determined by the Radamaca complexity, this expected supremum of the Radamaca process. Okay, so we should understand that if we want to understand these uniform laws of large numbers. All right, so let's go back to the learning problem. We've been talking about these abstract classes G and the inputs Z, but in our learning problem, G is the loss class composed with the function class. The loss function, I'm sorry, composed with the function class. So it's, you know, the loss incurred by different prediction rules in our class F. And Z is the set of X, Y pairs. So, you know, we've got this tight relationship, not just with an expectation, actually, you know, it's concentrated as well. So the relationship between these maximal deviations between expectations and sample averages maximized over our losses incurred by prediction rules is tightly related to the Radamaca complexity of that class of losses. Okay, so, you know, in many cases, we can actually relate that to a corresponding complexity for the original function class, right? So one very nice example is the 0-1 loss, classification loss. Let's say in the binary case, so we're interested in a class of functions now that takes two values. We'll choose plus or minus 1 because it makes our life easy. And Y here is plus or minus 1. So we're looking at binary classification. Our loss is the 0-1 loss. So it's the indicator for predicting differently from the outcome. We can write that in this sort of linear way, bilinear way, I guess, as 1 minus the product of Y and Y prime. Since these are plus or minus 1, or divided by 2, right? Since these are plus or minus 1, you can do a case-by-case thing. If they're the same, this thing is 1 and our loss is 0. If they're different, right, this thing is minus 1 and our loss is 1. Okay, when we write it that way, that's particularly convenient for working out Radamaca averages because it's a sort of linear kind of beast, right? So the Radamaca complexity supremum over our class F of the alignment between these epsilons and the losses. When we rewrite our losses in this linear way, we get the 1/2 part gives us just these epsilon i's, and the minus y prime part gives us this minus epsilon I yi times f of xi. Okay, crucial thing here is, you know, our expectation is over the sample and the XY pairs and the epsilon i's. But, you know, think about what this distribution looks like here instead of, okay, so first of all, I guess I should say, we can upper bound this by triangle inequality to say, you know, that's no more than the corresponding thing for this term. So expectation of the supremum of the absolute value of this term, plus same thing for the second term. That second term looks a lot like a Radamaca complexity, but instead of having an epsilon I times f of xi, it's got a negative epsilon I times yi times f of xi. But who cares, right? We're taking an expectation. This thing has exactly the same distribution because each of these yi's is plus or minus 1, and minus epsilon I is something that's independently plus or minus 1. So the product of those things is uniform plus or minus 1, right? So we could replace this by another epsilon I, or epsilon I prime or something, and we have exactly the same distribution, in particular the same expectation. And so that's where the Radamaca complexity comes from, and the first term, you know, is something that rapidly goes to 0 as n grows. All right, so that tells us that the Radamaca complexity of our loss class is closely related to the Radamaca complexity of our function class for this particular example of 0-1 loss. We'll see that we can get a similar relationship between these two for continuous loss, Lipschitz loss functions. Okay. Let's see. Okay, so Jean asks, is it possible to extend the bounded differences inequality to the case when we only know that the xi's are bounded or sub-Gaussian and the function is continuous or convex? Okay, so, you know, there's a whole world of these concentration inequalities. There are, and the function f is continuous or convex, and these xi's are bounded and sub-Gaussian. Okay, so we'll say a little bit later on about sub-Gaussian random variables and concentration of sub-Gaussian random variables. And we'll see that we can so let me postpone that question, Jean, to when we do come up with some comments on sub-Gaussian random variables, and we'll see that you know, some of these sort of properties we can work with in that case. A lot of times the functions that we're working with are actually sums or weighted sums or something of that flavor. Something that's very nice about the bounded differences inequality is it lets us work with more arbitrary functions. So we're taking combinations of these x's that can depend in complicated ways on the different xi's, a much more complicated way than the sum. And in some sense, it shows that, you know, the fact that this gives us the same sort of result as a Hoeffding inequality, the same rates, shows that, you know, sums are in some sense the worst kind of functions for combining things in a way that satisfies these boundedness constraints. But that is a tighter condition than you know, the sort of conditions you need when you're considering averages of sub-Gaussian random variables, for instance. But yeah, let me say a little more about sub-Gaussian random variables when we get to that point. Okay, so the steps so far have got us bounding these maximal deviations in terms of the Radamaca complexity, the expectation of the maximum of this Radamaca process over the class F. How do we keep control of that? You know, what determines the size of that thing? So there are a bunch of different approaches. I'm not gonna say much about many of them. You know, we'll see that that if we're in the happy situation where evaluating our function class on a finite sample leads us to something that's always a small set. You know, when we look at those vectors of length n, we always get a small set of vectors. Then that's particularly easy. So that involves something called a growth function. At least in the binary valued case, it's been called that. But you know, works more generally than the case of binary valued functions. In that case, there's a combinatorial dimension that characterizes the way this growth function behaves. The Vapnik-Chervenienkes dimension that gives us a bound on how this set of vectors, the size of this set of vectors can grow. And you know, there's a lot that's known about this sort of quantity. You know, very beautiful theory there. I'll mention very little of that, but you know, maybe point out one or two highlights. There are also various ways that you can keep control of the Radamaca complexity of a class of functions in terms of, in some sense, the way that class of functions is constructed. So you can combine information about complexity of modules that you use in coming up with functions. And we'll see an example of doing that for some neural net classes a little later on. There are other notions of complexity that you can use, that you can relate to the Radamaca complexity. So there are upper bounds in terms of covering numbers. You know, the intuition behind a covering number is you want to find a way of approximating a set with a finite set, where, you know, for the level of as the level of approximation, as you get to be approximating more and more accurately, you know, you should expect to have to use a larger and larger set to approximate things. And so this sort of rate of growth of the size of this approximating set as the accuracy gets better and better is a closely related notion of complexity. You can get upper bounds on the Radamaca complexity in terms of something called the Dudley entropy integral. So the log of these covering numbers is a notion of entropy. You can think of it as the sort of number of questions, binary questions you need to get answers to in order to narrow in on a good approximation from your class. So there's an upper bound in terms of these covering numbers. There's a lower bound that's not quite matching, also in terms of covering numbers. So these things are closely related. In the case of real valued functions, there are combinatorial dimensions related to the Vapnik-Chervenienkis dimension, scale sensitive versions of the VC dimension that, again, tightly connected to covering numbers and Radamaca averages. I'm not going to say anything more about covering numbers or scale sensitive dimensions in these talks. Okay, but let's have a quick look at growth function and some of these combinatorial dimensions. So the growth function is for a class of binary valued functions. The growth function is the largest cardinality of these n vectors that we get when we evaluate our functions in our class on a sample of size n. So I didn't keep it on this slide, but you'll remember, this notation. This is saying take our class of functions f, take our sample x1 through xn, and think about the set of n vectors that we can get when we look at a function from our class evaluated, f at x1, f at x2, all the way up to f at xn. And then for all the different f's in our class, we get a bunch of vectors of that form. Now we're considering binary valued functions, so there are no more than 2 to the n of those vectors. The growth function is the largest cardinality we can get as we look at different x1 through xn. Okay, so it's always smaller than 2 to the n, but it might be much smaller. So thinking back to the original Glavenko-Cantelli theorem, which is about things being uniform over these indicator functions, right? And think about what the set of restrictions of these indicator functions to samples of size n are going to look like, right? So we take the indicator for x1 being less than some point alpha, indicator for x2 being less than alpha, all the way up to xn, right? So we get a bunch of zeros and ones. If you think about x1 through xn being ordered on the real line, then we might have the pattern, here's x1 all the way up to xn. If we consider an alpha that's down below them, below all of those, then the indicators are going to be 0. For that alpha, we get an all 0 pattern, right? So for that g of x1 through xn is all zeros. As we move the alpha up and consider different g's, we're going to have one of those values change to 1 and the rest will be 0. As we move it up past the second one, we're going to have 2 of them 1 and the rest 0, and so on. So you can see, we only have n distinct transitions from the all zeros through a bunch of initial ones and the rest zeros up to the all ones, right? There are n transitions across that range, so only n plus 1 possible patterns of values that we can get. The growth function in that case is just n plus 1. Okay, way smaller than 2 to the n. All right, that's a nice easy example. And actually, as long as you have a bound on the growth function that grows slower than exponentially in n, then you have a good bound on the Radamaca averages, Radamaca complexity. Right, so we've got our class of functions. Okay, we were thinking about zeros and ones, but actually real valued functions in a bounded range is fine. The Radamaca complexity is bounded by the square root of, ignoring constants, the log of this growth function divided by n. right? So as long as this log of the growth function is growing slower than n, that is, the growth function is slower than exponential in n, then we have something that goes to 0 as n grows. Okay. Why is that true? Let me say a little bit about this. Right. So it's relying on a result that says, if we have a set in Rn, so this set is going to be restrictions of our functions to endpoints. If we have a set in Rn that has a sort of diameter, right? It's maximum, I guess it's maximum squared norm of elements of that set. I've put some scaling in here divided by n. Is that right? Right, divided by n because we're considering, these vectors of length n. So this is sort of a scaling linearly with n kind of quantity. So this is the sort of maximum scale of our set. When we look at the maximal alignment between vectors in that set and these random plus minus 1 directions, we can bound it in terms of the scale of elements of the set, that's the R squared, and the log of the cardinality of the set. Actually, it's the set and negations of points in the set. Okay. So we're interested in restrictions of functions in our class to samples x1 through xn. And our functions take values in this interval 0, 1. So capital R here is always no more than 1, right? We've got n components here that are bounded by 1. And plugging that in, the Radamaca complexity is the expectation of this thing, which we can write when we condition on the x1 through xn as, no more than the square root of 2 times the R squared here is 1. The log of this thing is log of this cardinality, right? Or twice that, I guess, because we're taking the set of restrictions and its negation and their negations. Putting the expectation inside is Jensen's inequality. The expectation of the square root is below the square root of the expectation. And then, I guess same thing for the concave log function. Jensen's inequality tells us we can put the expectation inside. We're just going to be bounding this thing by an upper bound, but you can see that all of these different quantities actually provide upper bounds. And there are various situations where you can do better by taking account of the distribution, but we're ignoring that and saying, look, our growth function here is for all x1 through xn, this thing is bounded by the growth function. Okay, so that first step here, arguing that we have an upper bound on this alignment in terms of this quantity, is using a particular result for finite classes, right? This is the result we appeal to there. It's a result, without the absolute values, throw the absolute values back in, and that's where we get the union over elements of the class and negations of elements of the set A. So we were using this inequality. And let me say a little bit about how this arises. We've got I'd kind of promised I'd say something about sub-Gaussian, but I'm inclined to skip the proof here and just give you some little highlights of where the sub-Gaussianity of in this case the sub-Gaussian random variables are the epsilon i's. So this slide gives a complete proof of that inequality up to bounding a moment generating function in terms of this exponential. So let's take a look at that, and that relies on the sub-Gaussian, a sub-Gaussian property of the relevant random variables. Okay, so let's do a little detour into sub-Gaussian random variables. So we know that when we take averages of Gaussian, take averages of any kind of reasonably behaved random variable, and the law of large numbers tells us that we're getting nice convergence to the expectation. We can quantify that in terms of a central limit theorem, and actually we can be quite quantitative for finite samples if we have more information about the tails of the random variables that we're combining in this way. One kind of tail information is having tails that go down like e to the minus x squared, like a Gaussian's tails. You can define the notion of a sub-Gaussian random variable in terms of how the mass, how those tails decrease. Another way of defining it is in terms of an upper bound on the moment generating function. So the moment generating function of a random variable x, I guess here I've subtracted the mean, so centered random variable. Moment generating function is a function of this real number lambda. It's the expectation of e to the lambda times this centered random variable. Okay, so that's the moment generating function, because the derivatives at 0 of this thing, derivatives with respect to lambda, the various derivatives give you the various moments. So expectation of x to some power, of centered random variable to some power. Okay, so a sub-Gaussian random variable, one of these many equivalent definitions is one whose moment generating function has an upper bound that, so for all lambda, this moment generating function is no more than e to the lambda squared sigma squared over 2. All right, so this is a lot like what would happen with a Gaussian random variable with variance sigma squared. And we're seeing, exactly, so the parameter sigma squared is the thing that corresponds to the variance of a Gaussian random variable. And this is exactly what its log moment generating function looks like. So there's this whole family of distributions whose tails are no worse than a Gaussian in some sense. So certainly Gaussian is a sub-Gaussian random variable. A random variable that's bounded in some range is sub-Gaussian also. And they have this nice composition property that you can sum independent sub-Gaussian random variables and get a sub-Gaussian random variable, and the parameters, these variance-like quantities, add, right? So you can understand how the sub-Gaussian property gets propagated when you, for instance, take averages. This sort of computation of the moment generating function is a key ingredient in a proof of concentration due to Chernoff, where you look at probabilities of deviations and bound those in terms of expectations of exponentials of this form. There's a slick inequality of that sort that when you have this information about the moment generating function, so when you have a sub-Gaussian random variable, you can use this Chernoff argument to show that the probability that variable deviates from its expectation by more than some fixed quantity goes down like e to the minus that quantity squared. And the normalization, the constant in here is the parameter sigma squared. This is exactly the sort of tailed behavior we see for Gaussians. So for sub-Gaussians, we're getting very much like Gaussian behavior. So this was what I was referring to earlier in response to your question, Jean, where when we're summing up these independent sub-Gaussian random variables, we get something that's sub-Gaussian and the parameters add. You can say more about combinations with dependence, with limited dependence. There's a very nice, I guess in a couple of places, nice exposition of this. So there's a book by Boucheron, Lugosci, and Massa on concentration inequalities that covers these sorts of things. There's a very accessible text by Roman Verschinen on called something like high dimensional data analysis, high dimensional something. I'm embarrassed, I've forgotten the title. Very, very nice book that has a chapter on sub-Gaussian and sub-exponential random variables also, and all the tricks you can play in proving concentration of these things about their expectation. Okay, so appealing to these results, we have a bound on the Radamaca complexity in terms of the growth function. Going back to one of the examples we looked at, if we think about these step functions, we saw step functions on the real line. We saw that the growth function here is no more than n+1. So you can plug that straight into this inequality. We get, remember the inequality was of the form square root of the log of the growth function divided by n. So we get something that looks like 1 over n. There's a log n factor, which is nothing compared to our 1 over n. As another example, thinking about a particular finite class, certainly the growth function is no more than the cardinality of the class of functions. And so, for instance, if we have a class of functions that's parameterized by k bits, right? So to come up with a distinct function, you change these bits in our parameter theta. The growth function is bounded by 2 to the k. We plug that in, and we get something that's a bound on the Radamaca complexity that looks like square root k over n. All right. So in both of these cases, of course, as n gets large, the Radamaca complexity is going to 0, like 1 over square root of n. Okay, and this is just a bit of a summary of these various facts, right? Radamaca complexity is no more than square root log of growth function over n. Growth function is never more than the cardinality of the class, and as n gets large, that's what it's going to approach. It's never more than 2 to the n, but of course that's useless in a bound of this sort, right? That doesn't tell us we're getting our deviations down to 0. We just end up with a constant on the right-hand side. So all we need to get a useful bound here is that the log of the growth function grows slower than the sample size n. Okay, I have a question in the chat. Right, instead of the xi themselves, we might want to estimate functions of it, such as the variance. Yes. So yeah, that's a good point. And there are results about kind of combining sub-Gaussian random variables. For instance, taking products of them. Turns out that if you take a product, so a variance, for instance, is a variance of a sub-Gaussian. Involves squaring and for such things you can show that these are no longer sub-Gaussian, no longer necessarily sub-Gaussian, but they do satisfy weaker tail properties that are also useful. So if you check out the chapter, for instance, in Roman Verschinen's book on sub-Gaussian and sub-exponential random variables, it's I think very useful for the sorts of applications it sounds like you're interested in. Okay, so let's take another break. I think unless there are more questions, it was just a thank you. good. So let's take maybe what are we at? We're kind of halfway through. So I think I'm going to suggest we take a 30-minute break now. If anyone has any burning questions before we do that, now would be a great time to bring them up. Either just speak up or put them onto the chat. We've got a couple of little things to go on with before we move on to the next section, but I think it's a natural place to take a decent break. All right, so if we don't have any questions, all right, I'm going to see you in 30 minutes time. So, you know, the next integral multiple of a half hour. It's it'll be 7:30 p.m. for me.
Yep, I think let's start. Yeah.
All right, so we've seen that in terms of getting this Glavenko-Cantelli property, these uniform laws of large numbers over classes of functions, the Radamaca complexity is the right quantity. It's tightly coupled to those maximal deviations. We've seen that we can bound it in terms of the growth function. The growth function, it turns out, for binary valued function classes is very closely related to the VC dimension, the Mcdiamond dimension. So let's quickly take a look at that. So we've got a class of 0, 1 valued functions. The VC dimension of that class is the size of the largest shattered set, where a shattered set is a subset of its domain where the subset of its domain of size D, for which the growth function takes its maximal value, right? So you can get all 2 to the D distinct 0, 1 patterns on that set. Okay, so it's the biggest D where the growth function evaluated at D is equal to 2 to the D. So the nice thing about the definition of the VC dimension is that it tells us essentially everything there is to know about this growth function. So if the VC dimension, and this is a result from I guess the 60s in the original Russian article, and the translation was 1971 about Mcdiamond. So a VC dimension of no more than D implies that the growth function looks like n choose D. So it's no more than this sum of from I equals 0 to D of n choose I. And when n is bigger than D, that of course, that's the interesting case. That sum's no more than en over d to the d. So, you know, crucial part there is n to the power d. So d is the exponent of the polynomial rate of growth of the growth function. So that's an upper bound. And you remember when we were looking at the bounds on Radamaca complexity in terms of growth function, they're down here at the bottom, right? Radamaca complexity is bounded by something like square root of the log of the growth function divided by n. So having this polynomial rate of growth of the growth function means we get when we take logs, it's like a d log n over n that appears inside this square root. So something that looks vaguely like, I've written it here, something that looks vaguely like square root of d over n as the upper bound on the Radamaca complexity. So, and you know, it really is this very concise summary of how the growth function grows, right? So either the VC dimension is finite, in which case the growth function grows like n to the d, or the VC dimension is infinite, in which case the growth function is always growing like 2 to the n. And there's nothing else in between. There's no other rate of growth. It's this polynomial rate with an exponent of the VC dimension, or it's the exponential rate. Okay, so you know, this is a very nice result for the case of binary valued functions. It implies in that case, if we have a bound on the VC dimension, then the maximal deviations between sample averages and expectations look like square root d over n, where d is this VC dimension. Turns out there's a matching lower bound. You can show in the case where the VC dimension is d, you can come up with a probability distribution. Sorry about that. You can come up with a probability distribution for which these deviations are as big as square root d over n. So, you know, if you want this uniform convergence property uniformly over probability distribution, so here I've written, you know, no matter which p you have, this thing is still no more than ordered square root d over n. If you want that sort of property to hold uniformly over probability distributions, then the VC dimension is the right quantity. All right, so finiteness of the VC dimension is necessary to have this worst case, for the worst case p, have these maximal deviations go to 0. So in that sense, you know, it really characterizes what's going on. And in fact, you can say something stronger, that you know, we were looking at bounding these maximal deviations as a way of controlling the excess risk of an empirical risk minimizer. And this shows that excess risk goes down like square root d over n in the case of finite VC dimension. But you can also show that if you wanted to do that uniformly over probability distributions, if you wanted to have the empirical risk minimizer performing well for all probability distributions, then finiteness of the VC dimension is also necessary. So there is a probability distribution for which the empirical risk minimizer is going to perform badly in the case of infinite VC dimension. In fact, there's an even stronger result. No matter what algorithm you have, if you want it to perform for every distribution, if you've got an infinite VC class, then actually for any d, if the VC dimension is at least d, you can get a lower bound on the sort of excess risk for that algorithm. So there's no getting around it in the case of a binary valued class if you want to work with arbitrary probability distributions. Okay, and you know, just to give an example of the sorts of results that are possible for the VC dimension, if we think about a parameterized family of binary valued functions. So our function class is given by functions that have this vector theta of real valued parameters. So let's say p real valued parameters. Then, you know, it turns out you can get bounds on the VC dimension for this family, provided that the computation here is doesn't take too long in a certain model of computation. So if that function, that for any x, if you can compute this function in no more than t time steps, t operations of these different kinds, so they're arithmetic operations on real numbers, comparisons of real numbers, and outputting plus or minus 1, right? Then in that case, the VC dimension of the class of functions you can compute with these p parameters in t time steps is bounded by something like p times t, number of parameters times the amount of time it takes to compute one of these things. The reason for that is that this class of functions is essentially polynomial in its parameters. So, you know, apart from the division operation, you're just computing polynomials here. You're doing comparisons, so you can have multiple polynomials floating around. you know, the degree of the polynomials can grow exponentially with t because you're doing multiplications, but still they're polynomials of bounded degree. It's a bounded number of polynomials, you know, maybe an exponential number that are involved. Those are the things that go into the computation of f, and in such cases you can get a handle on the VC dimension by thinking about how rich the class of functions is in terms of the sign assignments you can get, the mapping from the parameter space to the sign of the output. You know, is just all about the number of connected components when you remove the sort of polynomial boundaries between places where you switch the output of the function. So, you know, it turns out there's very elegant argument that gives you a bound on the VC dimension in terms of number of parameters times the number of time steps in this model of computation. So that's often very useful. The fact that the model of computation only includes the arithmetic operations is somewhat limiting. So for instance, you know, you might want to compute a softmax somewhere in your parameterized family of functions with an exponential. That's not included. Turns out the exponential is okay to add. You can modify the model of computation and get a related result, and that's due to Karpinski and McIntyre. It grows faster as a function of the number of parameters. It's like p squared in that case, but you know, you can get a bound. But you know, the functions that you can add, the modifications you can make to this model of computation are actually rather limited. For instance, you can't add the sine function, or suddenly with 1 or 2 parameters, you can have a function class that has infinite VC dimension. So, you know, it's sort of a brittle thing, and what's at play there is that the VC dimension for a class of functions like this is sort of a measure that can be arbitrarily fine-grained because you're thresholding things and making decisions, you know, plus or minus 1 decisions. You're really looking at very, very fine-grained properties of the functions here. So, you know, it turns out in this polynomial case, having not too many parameters suffices, but you know, even in that case, it may be a pessimistic upper bound in the sense that, you know, you are exploiting in considering the VC dimension, and for instance, in looking at those lower bounds I mentioned, you're exploiting sort of arbitrarily fine-grained properties of the functions that you're computing. Okay, so let me say a little bit about some structural results for Radamaca complexity. So how to compute Radamaca complexities by combining functions into a function class. And we'll see some examples of this in the neural net setting. Okay, so you know, here's a list of 5 properties. The first couple are really pretty simple. If you've got a smaller class, the Radamaca complexity is smaller. This makes sense. You're just taking a supremum, you know, maximizing over this class of functions. If you're allowed to maximize over a bigger class, you should be able to do, you'll certainly be able to do at least as well, and possibly better, you know, get a bigger value. The second one is that if you take your function class and multiply it by a constant, then because this Radamaca complexity is scales with the size of the functions, you can pull that scaling out front, right? It's the supremum of the averages of these epsilon i's times f of xi. If you scale f up by a constant, the whole thing scales up by a constant. Okay, so this third one is saying, you know, if you have a class of functions and you add on any fixed function, then the Radamaca complexity is not very different from the original class, right? So adding a function in, a bounded function, changes things by a sort of 1 over square root of n kind of level. The fourth property is that the convex hull is you can take the convex hull of the class, and that doesn't change the Radamaca averages. So we'll take a look at why that is on the next slide. But you know, this means that you get sort of convex combinations of functions in your class for free. It's essentially because of the sort of linear, the fact that you're maximizing a linear criterion here that's responsible for that. And the last one looks a bit technical. You've got a function phi here, and you want to think of it as just passing. I mean, this is making things a little more general, but think of it as passing functions through this phi. Then the Radamaca averages of these functions, right, compositions of your original functions with some function that is Lipschitz here in F, right? It's, let's say, 1 Lipschitz, then the Radamaca averages of these transformed versions are bounded in terms of the original ones with a constant of 2 here. And of course, you know, if you scale this up by a constant, then using this second property, that means you should scale up the Radamaca averages by a constant over here, right? So if the Lipschitz constant is B, then you should get 2B times the Radamaca averages of the original class as an upper bound. Okay, and this is called the contraction inequality. It's due to Ledoux and Talleyrand. Okay, so I mentioned the first and second were really simple. When we add in a function, you know, we can just use a triangle inequality here, right, to separate out what happens for our functions from our class and what happens for our single fixed function G. We can add them in and get, you know, that this piece in our triangle inequality, so it's upper bounded by that plus that piece. This piece is our original Radamaca averages. This piece is just a fixed function that has a certain scale. I think we said, yeah, bounded by 1, and we're taking that fixed function bounded by 1 and plugging it in, looking at its alignment with epsilon I. All right, so that's something that's you know, no more than the absolute value of this sum times the scale of the G, which gives us the 1 over root n convergence in that case. Okay, and the fact that we can take the convex hull without paying any price in the Radamaca complexity is because we're maximizing a linear criterion here, and doing that, you know, in a convex set, we're always maximizing it at an extreme point, which will be, you know, one of these, one of the generators, one of the functions in F. So the convex hull is certainly a bigger class of functions, but it doesn't have a bigger value of the Radamaca complexity for that reason. And the contraction inequality has an elementary proof, but I'm not going to go into that at all. Okay, so just to summarize what we've seen for the Radamaca complexity, if we're interested in these maximal deviations between expectations and sample averages, they're tightly concentrated around their expectations, and their expectations are closely related to the Radamaca complexity. All right, so the Radamaca complexity is really the right quantity in terms of understanding the maximal deviations. The VC dimension gives us an upper bound on the Radamaca averages. If we're interested in having this sort of uniform convergence property hold for every probability distribution in the case of binary valued function classes, then finiteness of the VC dimension is actually necessary for the worst case probability distribution. So it gives us a lower bound in that case also. Okay, this was where I was planning to have the long break. We got to this point a little slower. That'd be a good moment for any questions if there are any. Doesn't look like it. All right, so we can go on and look at some of the applications of these results to neural networks of various kinds. So, all right, so let's take a look at neural nets. Of course, you've all seen the big successes of deep neural networks. You can think of these as compositions of nonlinear functions that are of the form, take a vector input here for each stage in the composition. I guess I've written M layers here for the ith layer. You're taking a vector input, you're multiplying it by a matrix Wi, and passing that through a nonlinearity. The nonlinearity is something that's applied component-wise. So the ith component of the output is this sigmoid nonlinearity applied to the ith component of the input. Of course, other nonlinearities are possible. The point is that's something that's fixed, and the Wi is the parameter, the set of parameters for the function computed at the ith layer, and you're computing compositions of these parameterized functions. Okay, yeah, that's the sigmoid function. More popular at the moment are these ramp functions, the ReLU, the rectified linear unit, which just takes a max of 0 and the input value, again applied component wise here. So these are piecewise linear things. So if we think about this sort of network, it's a piecewise linear function applied to a linear function of the input, and then you compose those. So the whole thing is going to be piecewise linear, clearly. And, you can think of each of these as being just comparisons of real numbers. Everything going on here is just multiplying with parameters. So, the result that we saw earlier about bounding VC dimension certainly applies in this sort of a case. Here we need something more refined, as I mentioned. Okay, so let's take a look at some of those VC dimension results. So if we think about a network of that sort, if it's got L layers and P parameters, and in some cases we need to know the number of units, the number of nonlinearities that are applied, then the VC dimension bounds that are known depend on the nonlinearities. As I mentioned, if you throw in a sinusoid as your nonlinearity, you can immediately in 2 layers with 1 or 2 parameters get an infinite VC dimension. Okay, for the case of a piecewise constant nonlinearity, so just a threshold function, Baumann-Hausler in a paper back in 1989 showed that the VC dimension is of the order of the number of parameters. It's actually number of parameters times the log of the number of, it's p log k in this notation. You can show that that's a lower bound too. There's an order of p log k. For the piecewise linear case, you can use a refinement of the Goldberg and Jerem result that I mentioned to show that the VC dimension is of the order of p times number of parameters times the depth. And actually, although the notation here is not showing it, this should be a theta, right? There's a lower bound of order p times L as well. So that dependence on depth, it's more than just proportional to the number of parameters. It actually grows with the depth. For the piecewise polynomial case, there are bounds of the form p times depth squared, and again, this is building on the tools that Goldberg and Jerem introduced. That is only an upper bound, and the best known lower bound is order p times depth. So there's that gap between the two. We don't actually know if introducing, for instance, a piecewise quadratic nonlinearity increases the VC dimension significantly as a function of the depth. We certainly know that for the piecewise linear case. And the sigmoid, all we have is an upper bound that's, as I mentioned earlier, order of the number of parameters squared times number of computation units squared. Again, this is an upper bound, and the best lower bound for that case is actually the same as the best lower bound for this case, which is the matching lower bound for the piecewise linear case. So there's a big gap between order p times depth and order the p times depth lower bound and the p squared times k squared upper bound. Anyway, so kind of smorgasbord of results there for different nonlinearities. Interesting how they vary things. One kind of bottom line there is that actually all of these grow at least as fast as the number of parameters. So in terms of that measure of the complexity of the class of functions you can compute, you have a complexity that's growing at least linearly with the number of parameters. In terms of our upper bounds on the performance of an empirical risk minimization approach for networks with binary outputs, this upper bound is going to be of the form something like square root of number of parameters divided by sample size, depending on the nonlinearity, perhaps even bigger than that in terms of its dependence on the depth of the network. And those lower bounds that I mentioned show that if you want to work with any probability distribution doing empirical minimization over networks of this sort, actually using any algorithm to compete with the best network of this sort, you really need a sample size that grows like the number of parameters. You really need that excess risk really does, it can be as large as square root of the number of parameters divided by the sample size. So, okay, so that's the case of binary output networks. It turns out that these are not, we have a question in the chat. Russell, doesn't the Goldberg and Jerem case apply directly to the ReLU, since it can be expressed via comparison and a product, or is Harvey et al. Tighter than this application? Yeah, so that's right. That's exactly right. If you apply the Goldberg and Jerem result, it's number of parameters times the time, and back in that setting, the number of parameters here is p. The time that you take to compute is something like p. So you get a p squared sort of upper bound here, but you can do better. And you can actually, so this paper back in '98 was an improvement on the Goldberg and Jerem result for piecewise polynomial networks that exploited the fact that, in these networks, you're constrained in the sorts of sets of polynomials that you can work with. When you think of them as polynomials in the parameters, and so this thing only grows as p. There actually is a lower bound. There is a lower bound result in the Goldberg and Jerem paper that says, in general, you can come up with classes of functions that show that you can't improve this p times t, the time bound, by more than a constant. There's an example exhibiting the dependence on t, which in our case would be a p squared, but in this case it happens to be loose. You can do better. So yeah, that was the step forward in this paper, and the step forward in this paper was in two directions. It was getting an upper bound that was only linear in the depth, that was exploiting the fact that actually the degree of these polynomials, they're always degree 1, all the way through the network. So you can, although they're high degree polynomials in the parameters, they're degree 1 functions of the input. So I guess the other, there's a, so you get an improvement in terms of the dependence on the depth, and the other contribution of this paper was a better lower bound. I mean, there are various refinements that this result is covering a lot. It is hiding a lot in the sense that VC dimension there depends also on the distribution of the parameters, right? You get this full depth dependence if the parameters are concentrated near the beginning. If many of them are near the end, you don't have it's not as large, right? Things can be simpler when most of the parameters are close to the end, to the output in some sense. So there are various refinements of that sort. But yeah, you're absolutely right. You can get a result immediately from the Goldberg and Jerram theorem. Okay, so just going back to this conclusion, the punchline there was this VC dimension is always at least linear in the number of parameters, which suggests you should have a sample size that grows, proportional to the number of parameters and maybe as something bigger. But even back in the 90s, this was already clear. This was not true. So this is actually, not showing the neural net example first, but this is I guess you can think of AdaBoost as producing a two-layer neural network. It's producing a combination of classifiers from some class. If that base class is something like a decision stump or a linear threshold unit, then you really are producing a two-layer neural network. It does it in a sequential way. Bagging is doing something similar with a different algorithmic approach. So this is Wei Sun was an author on this paper. So this was an observation back in the late 90s that actually these approaches, the plots here are showing as these algorithms proceed. So this is iterations of the algorithm. The bottom line is the test, the empirical risk, and the top line is an unbiased estimate of the risk. And you can see, the somewhat surprising thing here is that you should be expecting as the number of parameters increases, certainly the VC dimension of this class of combinations of decision stumps or two-layer neural nets, with 10 units, if you like, in the first layer, 100 units, 1,000 units. This VC dimension is growing for a fixed sample size. You should expect your generalization error from the VC bounds to be degrading. And even if it's not, the performance on the training sample, the empirical risk, is stuck at zero. You've done the best possible on the sample. You're correctly classifying everything, and yet the performance on the test is actually improving. Similar thing in the bagging case. So the observation that suggested what was behind this was, if you looked not just at the empirical risk, that is whether you're getting the examples correct or not, but if you looked at the margin of those correct classifications. So that is, if you want to get to the +1 side, how far are you to the positive side? If you want to be on the negative side, how far are you on the negative side? And these bottom plots are showing cumulative distribution functions over the training sample of those margins. So as soon as everything, this dashed line, I think, was from this first point when you hit zero empirical risk. As soon as everything was to the right, to the correct side with a positive margin, that's that line. As the number of iterations increases, this thing converges to a distribution that's really pushed quite far away from zero. Similar observation in the bagging case, which is a less directed version, but similar sort of properties and similar behavior. So this is related to the comment I made that the VC dimension is really capturing fine-grained properties, and if you were exploiting the full power of this class of functions and minimizing, working with that full family of functions, you might not expect to see this sort of behavior. But we're actually working with the real valued functions and performing some sort of optimization over those. And so we are playing with the margins here. We're not just looking at the empirical risk. In which case, if we were, all of these functions would be indistinguishable. Okay, so this was the neural net example from about the same about the same time where people observed that, you know, despite this theory that suggested that the sample size should grow with the number of parameters, you know, you could keep on increasing the number of parameters. In a face recognition example, for instance, you know, it's 2 to 3 orders of magnitude more parameters than training points, and you're still getting a continuing improvement in performance. Here are more recent observations of the same flavor for deep networks, right? So where the number of parameters is being increased on this x-axis, and again, the black line is training, is empirical risk, and these other lines are, I guess the blue one is the thing to look at, are the unbiased estimates of risk. Okay. So I mentioned this margin distribution. You know, in these cases, we're actually using real valued functions for classification. We're predicting with the sign of those functions. And so this quantity that I was plotting was y times f of x. So when y is plus or minus 1 and you're interested in the sign of f, you know, you want this thing to be positive. That corresponds to a correct classification. But the losses that are being minimized here are actually, you know, continuous functions of the margin of this function on the point xy. And you know, they're losses that encourage larger margins. So things you might interpret as more correct classifications in some vague sense. So certainly, you know, minimizing continuous losses like the quadratic loss or the exponential loss that AdaBoost uses. And of course, for the case where y is plus or minus 1, you know, you could rewrite this as yi times f of xi minus 1 all squared, right? Just because yi squared is a constant. So both of these are encouraging, you know, they're nice, continuous, even Lipschitz functions of the margin. They're encouraging large margins. And in such cases, we should expect the kind of fine-grained details of our functions to be less important. The sort of details that the VC dimension might capture, you know, perhaps shouldn't be so important if we're working with a loss like this. Okay, that's the intuition. Let's look at, you know, what kind of theorems we can prove. Going back to this last structural result for Radamaca complexity, right? That said, basically that if you have a function that is Lipschitz in, so if phi is Lipschitz in the f value, then when we compose functions in our class with phi, we get a Radamaca complexity that doesn't increase too much, right? It'll increase by a constant factor that depends on the Lipschitz constant of that function we're composing things with. We have some technical conditions. You know, we want phi to be 0 at 0, right? And it's Lipschitz in its first argument for all of that second argument. Okay, so let's look at a specific example where, and this is bounding the Radamaca complexity of the loss class, right? So this is the composition. I've written it in a slightly different way here. I apologize for the change of notation. The class we're thinking about now is the composition of our functions with the loss function, and I'm going to subtract the loss when f is 0, just so that when the my function phi takes value 0 when its first argument is 0. This is the technical condition we need. Okay, so, you know, but all I'm doing is adding in some fixed function. It doesn't make any difference. It doesn't make any significant difference. So this is our loss class now, modulo this fixed function. And, you know, we saw that we needed the Radamaca complexity for the loss class to be small in order to have, you know, maximal deviations between expectations and sample averages for these losses. So risk versus empirical risk, small. We can immediately apply this result to say, you know, that thing, if this is a Lipschitz function, if L is 1 Lipschitz, then we get a bound in terms of the Radamaca averages of the original class, right? And, you know, if the loss is bounded, this second fixed function doesn't change anything, right? So we just get a, the loss class is the same as this phi of f plus an L0 function, which gives, remember, gives us this other little piece, the 1 over square root of n piece from this third result here. Okay, so why am I telling you this? This is how we can convert a loss function, a class of loss functions, the Radamaca complexity for a class of loss functions to the Radamaca complexity for the original class. Well, so this is going to be an important tool in understanding the margin, the large margin case, right? So classification loss is certainly not Lipschitz, but if we're working with margins, then we can consider a Lipschitz loss. So, you know, there's a nice intuitive way of seeing that. So, you know, remember y times f of x is our margin. We want to be to the correct side of 0. So we want y times f of x to be positive. Y is plus or minus 1. We're classifying with the sign of f. So this black line is the function that corresponds to the indicator for making a mistake, right? We make a mistake anytime we're over here and we're correct over here. So the expectation of this loss, the black loss, is misclassification probability. That's what we're really concerned with in this problem. We've designed this red line, and this is a trick introduced by Kolchinsky and Panchenko. We've introduced this red line as a Lipschitz loss function that's everywhere at least as big as the indicator, as the mistake function, right? And that Lipschitz loss, you know, it's 1 to the left of 0, it's 1 to the right of gamma, and it's, you know, piecewise linear. Okay, and then the dashed blue line, that's the indicator for having a margin less than gamma, right? So when we want a large margin, you know, we want to be out in this region, right? We want most of our points out here. So this is a loss that counts a 1 for every point that's closer than gamma to 0. And you'll see that it's bigger than the Lipschitz loss everywhere, or at least as big everywhere. Okay, so now we have these 3 loss functions floating around. We can compare them, right? When we're considering large margin loss, that's looking on the sample at points that have margins smaller than gamma and penalizing them. Well, that, as we saw in the diagram, is an upper bound on this Lipschitz loss. And that Lipschitz loss is an upper bound on the misclassification indicator, right? So the piecewise linear, you know, Lipschitz function lies between the indicator of making a mistake and the indicator of having a margin that's not bigger than gamma. So, you know, so we can use this fact to get an upper bound on this quantity in terms of that quantity. How do we do it? We say, well, the expectation of this quantity, so that's the probability of making a mistake, that's our risk. That's upper bounded by the expectation of this thing that's above it everywhere, right? That thing is a nice Lipschitz loss. All we have to do is relate the true phi risk, right, the expectation of this quantity, to the empirical phi risk, so the sample average of that quantity, and we'll do that using our maximal deviation results in terms of Radamaca complexities. And then that quantity, phi, is upper bounded by this indicator for the margin loss. And so sample averages of phi are certainly no more than sample averages of these indicators. So as long as we can control the relationship between this expectation and its sample average, then we've got an upper bound on the probability of misclassification in terms of the proportion of examples that don't have this nice big margin of gamma. Okay. So, you know, just writing those inequalities out, we saw all of these, and the crucial one that I'm adding here is this one, right? That the expectation of phi is no more than, you know, these two are close uniformly over the class in terms of the Radamaca averages of this loss class, the phi class. But we saw that we could bound that in terms of the Lipschitz constant of the class times the Radamaca of phi rather, times the Radamaca averages of f plus a little bit. Okay, so remember phi is this function that goes, that's flat up to 0, flat to the right of gamma, and it has slope 1 over gamma in between, right? So the Lipschitz constant is 1 over gamma. We're paying a price as that gets steeper. We pay more and more of a price as this thing gets closer to the indicator for making a mistake. And of course, this thing is upper bounded by the indicator for not having a big margin. Okay, so now we've got this upper bound that we want, and it's in terms of the Radamaca complexity of our real valued class, scaled by something that depends on the margin. One way to view this is that we've turned our classification problem into a regression problem, right? We're really working with these real valued functions. And you know, the VC dimension was relevant if we were working with thresholded versions of our functions. And you know, this is a thing that captures these sort of arbitrarily fine-grained properties of the function class, but it might not be important on this side, right? It may be that our real valued function class, before we threshold it, has much lower complexity, and we'll see a few examples like that. Okay, here's a very nice one, nice simple one. Consider the class of linear classifiers. So I guess this F is the class of linear functions of bounded norm. Let's say the norm is 1. So X here lies in Euclidean space of dimension D. Maybe it's even infinite dimensional. Let's keep it at dimension D. And our functions here are just, you know, the inner product between this parameter vector W, which has norm no more than 1, and the input X. Okay, so, and we're thinking about the case of classification by thresholding these functions. So it's an easy calculation to show that the Radamaca averages for this class are bounded by, you know, 1 over square root of n, something of that order, constant over square root of n. And so, you know, plug that into the result up on the previous slide, and we get this was the misclassification probability. So the risk of a function chosen from this class is no more than, and I'm suppressing constants here, I guess constants in this term, so it's a little misleading, is no more than the average of these indicators of having a margin less than gamma, plus something that's like a constant divided by gamma square root of n. So if we have good large margin performance here, then actually, you know, this class has a bound on its risk in terms of this empirical margin-based loss that looks like, you know, 1 over square root of n times this 1 over gamma. There's no dimension here in sight, right? If we were considering the class of thresholded functions and trying to relate the risk to the empirical risk for that class, we would have a square root d over n in here, all right? But there's no dimension dependence at all. So it may be, you know, if we find a function with unit norm, one of these linear functions with unit norm, so that when we threshold it, we get a nice big margin, you know, we get a 1 over square root of n sort of a rate, and we escape the dependence on dimension. Okay, so what I've been talking about here is just an upper bound, right? So we've seen that, you know, you can get a loss, a bound on the expected loss, on the risk, in terms of the sample average of this margin loss, plus a complexity penalty term that depends on Radamaca averages of the class and depends on the margin. That's just an upper bound, but it turns out that you know, you can get tight relationships, not between the kind of surrogate loss. We call this, you know, margin loss a surrogate loss. You know, the results that we've got are not. What we know is that you can relate the not the risk of a function to the risk in terms of the expectation of some surrogate loss, but you can relate the corresponding excess quantities. Excess over what? Over the best possible, not just with your function class, but with any function class. There's no actual actual restriction to a class of functions in this theorem. What we're saying is, so L star here is the minimal risk over all measurable functions. So the very best you can do, with complete knowledge of the probability distribution and no restriction to any function. You just want to have your expectations defined. You can show that for any surrogate loss phi, this is the expectation of that loss for our function f. This is the minimal value of that expectation for any measurable function. So this is kind of an excess phi risk. For any phi, you can define a transform. There's a specific recipe for coming up with this psi as a function of our surrogate, so that you can relate the excess risk over the optimal to the excess phi risk. And it's written in this way because, it turns out if you choose a surrogate loss badly, then, this quantity can be big even when that quantity is zero, right? So you may have chosen phi in such a way that you got the risk right down to the optimal value, but you still didn't do very well in terms of the risk here. So, but it turns out, that under some easy to check sufficient conditions, driving the right-hand side to zero implies you drive the left-hand side to zero. So for instance, if phi is convex, then for that to hold, it suffices that phi is differentiable at zero and has a negative gradient at zero. So when you compute phi of the margin, in that case, you have some convex function that's pointing the right way, that's driving you to big margins. Okay, so you can get explicit relationships of this sort, and it turns out they're tight. That for any excess risk, let's say theta, you can come up with a situation. Under mild conditions, you can come up with a situation where the excess phi risk is very close to this transformed version of theta. So this is not an inequality that you can improve point-wise anyway. Okay. Point to pause for any questions. Okay, so that's large margin classification. That's all I want to say on that topic. Let's see. I guess I've gone. I've gone on for quite a bit longer than I had planned. Okay, let's do Radamaca averages for sigmoid networks, and we might have a longer break for questions there. Okay, so we talked about some of these VC dimension results for neural nets. We talked about these sort of anomalies that it looks like, the VC dimension is not capturing the kinds of notions of complexity that are important in these cases. And we've seen that, actually we can get around that in the case of classification, large margin classification. So if we're working with a loss that's continuous, it turns out we can get bounds on misclassification probability in terms of these margin losses. And the complexity that arises is the Radamaca complexity of the class of functions, appropriately scaled by the Lipschitz constant. And of course, if you're in a regression setting and the loss is Lipschitz, then it's the Radamaca complexity of the loss class that we saw is important, and passing your functions through this Lipschitz loss means we can invoke the contraction inequality and bound the Radamaca complexity of the loss class in terms of the Radamaca complexity of the class of functions. So in either case, we're left with this question: what's the Radamaca complexity for natural neural net kind of classes? So we can use the tools that we've met along the way to compute bounds on Radamaca averages for various networks. Okay, so let's look at, here's one example. And this, I guess, dates back to the, well, no, I suppose a calculation of this sort dates back to the 90s, but doing it in terms of Radamaca averages is a much easier job than the kind of covering number analysis from the 90s. So, okay, so we've got a class of two-layer neural networks. The thing about this class is that we're not constraining the width of the first layer. We're considering functions that map from a vector input x through these, I've written it as separate inner products, k separate inner products, v1 through vk. Are the parameters of those. We take the inner product of that with our input x, pass that through a nonlinear function, and then take a linear combination of those things. Okay. I don't know why this is a typo. There is no need to have the wi's positive here. So that should not be there. This is just there are constraints on the scales of these parameters, and for convenience, we've made them both the same. They're capital B, right? We're measuring the scale in terms of the one norm of the parameters. So every parameter every parameter vector in the first layer has a one norm bound of B, and the vector of output parameters has a one norm bound of B also, and K can be anything. So we're allowing any number of these first layer units, but the parameters are all constrained in this way. And the other thing we have is that the function sigma satisfies a Lipschitz condition, right? And I've just written it as a one Lipschitz condition, right? As you change the input by some amount, the output changes by no more than that amount, 1 times that amount. I guess we're getting around the sort of complication of applying the contraction inequality by assuming that sigma of 0 is 0, although this is not very important. Okay, and our inputs are bounded in L infinity, let's say. So all components of the input is bounded. Each component is bounded. Okay, then the Radamaca complexity of this class is no more than something like b squared over square root of n. There's the dependence on the input dimension is like logarithmic, right? So b squared square root log d over n, where d is that input dimension. Okay, and in particular, no dependence on k, of course. It's just the scale of these parameters, product of the bounds on the scale of these parameters that arises. Okay, so let's take a look at why that's true. So we have here just to introduce some notation. We can think about these having a one norm bound of B as having something like a convex combination of functions scaled by B. So okay, we met this notation earlier. The convex hull of a class of functions is the set of convex combinations of functions from that class, right? So these alphas are non-negative and they have a one norm of 1. They sum up to 1. Okay, so now I want to just introduce some notation so that we can, compute the Radamaca complexity using the tools that we've met. So let's think about this class of functions as a kind of composition of function classes. So we start off with the original input vectors. Let's think of those as being, having separate components, and we're going to call that a function class, right? It's a function class of size D. Each function in that class takes an input vector and returns the jth component. And so there are D distinct values of J. That's our class G. I want to think about the class of first layer functions before the nonlinearity, so these things, as a convex hull, right? So that class of functions I'm going to call VB. It's the functions that map from an input vector to the inner product between this parameter V and the input X, where the inner product has a one norm constraint, right? The one norm of V is bounded by B. That's what's going on here in our two-layer class. So I can think of this as scaling these things by a constant B and then having a one norm constraint of 1. Well, then I'm taking just a convex combination. With a one norm constraint of 1, I'm taking a convex combination of these components of X, right? Because I put absolute values here, because I'm allowing negative values of the V, it's actually a convex combination of components of X or negations of components of X, right? I'm allowed to combine them in a convex way. And actually, because I have an inequality here, I'm allowed to take a convex combination of these components or the zero function. Okay, so I have the convex hull of these things, because I've made things symmetric, this is redundant. And I just have B times the convex hull of my coordinate class union the negations of the elements of the coordinate class. So this is just another way of writing the class of first layer functions that I have. And then I'm taking those first layer functions, I'm passing them through a Lipschitz nonlinearity, and then I'm taking those K distinct functions and I'm combining them again with a scaled convex combination. All right, and so okay, so I did actually maintain this positivity constraint, but you can see we don't need it, right? We could have done the same trick by negating these things and had a convex hull of a union of this with its negation, but we didn't do that. So, okay, fine. I left the positivity thing in there. But it's exactly the same thing, right? I'm taking effectively a scale because I've got the sum of these things being no more than B. I've got a scaled by B convex combination of functions that consist of Lipschitz nonlinearity composed with functions from this class. And because it's an inequality and not an equality, I can take the zero function as well if I like, which is just equal to, but it doesn't change anything. This is just B times the convex hull of this class. So now we can just go through and use these hammers that we've developed, right? The Radamaca complexity of our class of two-layer functions, we can write it in this way as scaled convex hull of this class. So we know how to deal with the scaling, that just passes right through. We know how to deal with a convex hull, that doesn't change anything. We know how to deal with a Lipschitz nonlinearity here, that gives us an upper bound through the contraction inequality. This, remember, was Lipschitz constant 1. And now we've got our class of VB, the first layer function. Okay, so we can rewrite that class as B times this convex hull. The B we know passes right through, gives us a B squared. The Radamaca complexity now of the convex hull is the same as this class, right? Doesn't change anything. And now we've got a Radamaca complexity of a finite class, a class of size 2D. Remember, this class G is the class of coordinate functions. So this is just B squared square root log D over N, which is the result we wanted. So you can see, these sort of structural results make it very easy to compute Radamaca averages for functions of this sort, function families of this sort. Okay, I'm going to skip over that. So there are results about ReLU networks. I'm going to tell you about this ReLU, this result for ReLU networks that exploits the positive homogeneity property in kind of a neat way. So okay, this is, so what's the positive homogeneity property? So the ReLU nonlinearity is this one that's 0 to the left of 0 and the identity to the right of 0. So it has this nice property. If you scale things by a positive constant, you can pass that through the nonlinearity, right? 3 times the input passed through the ReLU. You know, it's either passing through the 0 function on the left, to the left of 0, which is still alpha times 0, or it's the x function to the right of 0, which is alpha x function, which is alpha times the identity function. So we have this nice property that, you know, we can scale, we can shift the scaling from input to output. So that's something that actually, you know, you can rather easily exploit in computing Radamaca complexity. So, okay, so let's look at this example of a class, and it's taking a slightly different notion of the scale of the parameters that appear. All right, so I'm using sort of slightly different notation, so you don't have the summation. We're thinking now of these ReLU nonlinearities as being applied component-wise. So we take our input vector x, multiply it by a matrix W1, and then component-wise we're applying the ReLU function, the ReLU nonlinearity, and continuing on that way, right? Linear transformation to another vector, apply this thing to the components of that vector, and so on. Okay, and for each of the parameters in these L layers, we have a bound on the Frobenius norm of the matrix. So that's the sum of the squared entries of the matrix. I guess square root of that sum is bounded by B. So all the way through the network, we have those bounds. Of course, we want a real valued output. So this is the row vector. And these things, you know, it's, I've said a fixed one Lipschitz positive homogeneous function, you know, that's essentially a ReLU, or you know, some sort of leaky ReLU or something. It doesn't allow any more freedom than that. So yeah, think ReLU for sigma. And the result is that the Radamaca complexity is like 2b to the depth L, the number of layers L, divided by square root of n. Okay, let's take, I have a question in the chat. Leaky ReLU is also absolutely homogeneous. Does the same theorem hold for leaky ReLU? Yeah, that's right. Yeah, all right. I'm late in answering it. Thanks, Russell. Yeah, so all we use is that positive homogeneity property, I guess, and the Lipschitz property. Okay, so let's see why this is true. So we're relying on this lemma, which we'll look at in a moment, and it's sort of the heart of the argument. The lemma says, you know, if we want to take the Radamaca complexity for a class of functions here, so think the functions you can compute up to the current layer of the network, right? Together with this linear function that we're computing at this layer of the network, and then the nonlinearity. So now we're looking at a Radamaca complexity for all the stuff earlier in the network and the stuff I'm allowed to compute at this layer. And of course, this layer has a Frobenius norm bound of B, you know, that's our class. So this is a way of sort of propagating Radamaca complexity results through the network, because we get an upper bound on the Radamaca complexity of up to this layer and including this layer, in terms of the Radamaca complexity of just up to this layer. Okay. All right. So, you know, this inequality, you can just iterate it forward, right? You start off with the functions being just the original x's and compute, you know, whatever this thing is when when there's no supremum here, right? Where it's just epsilon I xi, and then keep on iterating things, gathering a factor of 2b through the L different layers until you reach the output when you've got a supremum over the full network with all of the constraints. Okay, and so I guess that gives the 2b to the power L times whatever this thing is for the inputs, and that's a little calculation, right? So and it's an easy calculation, right? So this is the Radamaca complexity, this is the corresponding expectation of supremum goes away. Expectation of the average of this norm is, precisely, the expectation of the square root of that thing squared, the norm squared, right? Which you can pass the expectation inside, that's Jensen's inequality. The expectation of a square root lies below the square root of the expectation. And then that expectation you can compute, because these epsilon i's are independent of mean zero. So the cross terms have expectation 0, and we're left with epsilon I squared times the sum of these norm of epsilon I xi squared. Epsilon I squareds are just a constant 1, and we get the norm of xi squareds coming out. So this thing is just 1 over square root of n. These things are all like unit scale, remember? Okay, one thing I guess I brushed over. I didn't take any notice of the fact that these are norms here. This is a 2 norm that we're propagating, but of course, once you get to the output, at the output, the not quite like this. You lose the nonlinearity at the output, but the W is a row vector, and so its 2 norm is just its absolute value. So at the output, we've computed the Radamaca complexity. Because we have a scalar quantity, but all the way through we were computing kind of the vector version of the Radamaca complexity, and I didn't mention that earlier. I should have. Okay, so so this is sort of the crucial step, and why is it true? It exploits that positive homogeneity property in a really elegant way. So if we think about our W as having different rows, k different rows at each layer, and k is arbitrary here. It's just whatever the dimension is at that layer. We didn't constrain it. We constrained only the Frobenius norm. But we want the notation, right? Capital W has a bunch of row vectors, W1 through WK, and we're using those to compute, the corresponding component of the output of this layer that we're up to. So when we look at the norm squared of this quantity, we can just write that as the sum across the k components of these components squared, and now we can use the positive homogeneity property, because this Wj vector that appears in our row vector, the jth row of our matrix, we can scale that down by the norm of that jth row and throw the norm outside the ReLU nonlinearity. And so we get, this is inside a square, so we get norm squared here, right? So pushing it through means we're considering something that has unit norm and takes a linear combination of our inputs. Okay, so when we think about that supremum of this norm squared, and that was the crucial quantity, I guess it's the square root of that we're considering here. When we think about a supremum over the constraint on the Frobenius norm of this matrix of these things, that constraint on the Frobenius norm is saying actually all of these terms need to sum up to B. Okay, so those Wj squareds have to sum to B. Let's write each one of the norm Wj squareds as an alpha j, and the one norm of those alpha j's has to be B squared, no more than B squared. We're replacing this normalized vector by one that has norm 1, and we get a different, just a rewrite. All right, but now we've got something that's, a linear combination of stuff. We've got a separate optimization here and here, right? And clearly the right thing to do with the alpha j's, which have to sum up to b squared, is to put all of that b squared on the maximal value of this one, right? So so we can remove that maximization. It just becomes b squared times the biggest value we can get from any component here. And then what's the biggest value we can get from any component? Well, that's just, you know, like it's a squared Radamaca complexity for, you know, this ReLU nonlinearity, which is Lipschitz applied to these functions. The Lipschitz passes through the Ledoux-Talleyrand contraction inequality. And then we're just considering, you know, where we've got a norm of W equals 1 here. That thing just goes away, right? We're considering the in maximization of this thing, it should just be aligned with the direction of the f, and we get the norm of f appearing in here, the norm of this whole thing appearing in here, which is this term. So you know, really rather slick. We can take the scaling through and greatly simplify this optimization problem. Okay, and you know, of course, that gives us this result in terms of a kind of scale of parameters at each layer multiplied together, and you know, and there's a 1 over square root of n as well. Okay. So just to sum up this part, the and I think I'm going to have to end after this part. You know, we've seen that this large margin setting lets us turn a classification problem into a regression problem, and that's appropriate if we're using a loss function that's you know, continuous. And in regression problems, you know, the complexity that we get out of the Radamaca averages, it might be quite different from the complexity we see in a classification problem. You know, in particular, it can be controlled by the size of the parameters and totally independent of the number of parameters. So these last few examples have all had no constraint on the number of parameters, just on their norms. So, you know, there's this nice trade-off between the fit to the training data, you know, in terms of various kinds of losses and some sort of complexity penalty. You know, in the examples we've just been looking at, this is in terms of the size of the parameters that we see, and you know, that trade-off arises, gives us an upper bound on the risk, and so, you know, from those examples, the large margin, the ones that motivated the large margin classifier study, you know, even if that training set's classified correctly, we might get some advantage to increase this complexity penalty if we can improve this margin loss function. You might still get an improvement in this upper bound on the risk. So okay, so that's a point. That's a good point to stop. We still have 10 minutes for questions. I didn't get to the last section. The last section is on, you know, more recent work that's motivated by empirical observations that actually you can get pretty good performance even if you're fitting to the noise with a regression loss. So it's different from the large margin setting that we were talking about, in the sense that there, you know, those illustrations were for classification loss. You're kind of overfitting, fitting too well to the classification loss. But, you know, it turns out you can fit too well in the sense of even fitting better than the noise level suggests you should be able to, with a regression loss, and still predict accurately. To understand how that can arise, you know, all of the work that's been done to date has been really reliant on specific models of the process generating the data. So it has quite a different flavor from the work that the results that I talked about earlier. But I think it's very interesting. It's really a very different scenario in the sense that there's no trade-off between complexity and fit to the data when you're fitting the data perfectly. You can't possibly fit anything any better than coming up with zero loss. So there's been a whole flurry of work in that direction. We started looking at linear regression, as I say, with specific models for the process generating the data. There had been some work prior to that on variants of nearest neighbor methods that had similar sorts of properties, at least asymptotically in dimension, kernel smoothing methods, and then there was a whole flurry of work on linear regression sorts of problems and kernel regression problems, where let me pull up one cartoon here of the sort of the sort of high-level intuition here. In these settings where you fit too well to a regression loss in a noisy setting and still predict accurately, all of the cases that have been analyzed and that we understand have this kind of flavor that you can split the prediction rule you end up with into something that's simple in the sense of the sort of machinery that I've been talking about today, and useful for prediction. And then a second component that is hugely complex. It's useful for overfitting to the data, fitting to the noise, but it's benign. It doesn't hurt in prediction. And so things, really split into those two components. The first component, the classical statistical learning theory of the flavor that I've been presenting in these lectures really applies there. And the second component, is a totally new thing that's, as I say, not useful for prediction, but isn't harmful for prediction. It's only useful for overfitting. This is what we've seen, in kernel smoothing methods that overfit, that exhibit this benign overfitting. In linear regression in kernel settings, there, all the examples that we know about, and just to jump to the very end, in my last moments, you can see I was ambitious. Maybe I didn't. No, I didn't have it at the very end. Okay. Anyway, these are all linear cases. And I think what's really interesting is understanding what happens in a nonlinear setting, understanding what happens, for instance, with deep neural nets, which is the setting where this phenomenon was really brought to everyone's attention. And I think it's very interesting to conjecture perhaps it's a similar situation. Perhaps we have these two components, a component that's simple in some sort of classical sense, and another component that perhaps is complex and useful for overfitting, but not useful for prediction at all. And it may well be in a neural net setting that driving the empirical risk to zero endows some sort of computational advantage. So I think that's a really fascinating direction, but there's still lots that we don't know. Okay, so Manish asked the question: how does one approach models having something like 5 to 10 observations? Right. So you work with very simple models. Where I mean simple in the sense of the class of things you can represent. They may not be simple in some sense, right? So if you have a lot of domain knowledge and you need your 5 to 10 observations to effectively estimate, one parameter, you might be okay. One parameter in some very complicated system. Or if you're, working with without that kind of domain knowledge, then you really are restricted to doing very simple things.
No, so sorry. So this is something that I've come across a few times when in work, where we actually have pretty low samples.
Right.
And so one thing that we've tried to do is to basically run a simulation based on those 4 or 5 samples and their parameters. And from there try and, I mean, is that a valid approach? What do you think about that?
It depends on how much you know about the setting. If you know enough that you can run a useful simulation, then you're probably not in a situation where you're estimating most of what you need from the data. You probably have that in your simulator. So it depends on the setting, but if you're trying to work with big flexible models of the sort that a lot of the
no, that is not possible at all.
Yes, then you're in deep trouble with some few regulations, right?
Yeah, sure. Right, thanks.
Sure. All right. So Dan says, do these benefits of overfitting in recent works only stem from the use of gradient descent as an implicit regularization, or does it extend beyond gradient descent based trained models? Yeah. So that's a great question. There's kind of the realm of theorems, and then there's the speculation. So in the settings where we know what's going on, where we can prove things, the fact that you're working with gradient descent and it has some implicit regularization, you can study it that way, or you can say, oh, if I'm working with, let's say, linear regression with a quadratic loss, then certainly a gradient flow starting from the origin is going to give me the minimum Euclidean norm solution, right? So that's the implicit regularization for gradient flow for a least squares problem of that sort. And so you could consider that, or alternatively, you could consider just explicitly that optimization problem, the minimum Euclidean norm interpolating solution in a least square setting, and that's actually the problem that I was hoping to have time to present. So the thing is, I mean, I think it's a little distracting to call it implicit regularization as if you're imposing some regularization that's of the same flavor as the sort of regularization we're accustomed to in logistic regression or support vector machines or any of those cases. The level of regularization there is something that you can think of as, commensurate with the noise level. So if you think of a regularized empirical risk minimization optimization problem as equivalent to constraining the, I want to have my regularizer as small as possible, subject to the my regularization term as small as possible, subject to the constraint that my fit to the data is better than blah. That better than blah shouldn't be down way below the noise level. And here, when you're talking about the implicit regularization of gradient descent for a solution that fits the data perfectly, that's nothing like the regularization that we're used to. It's more like, what is this infinitesimal regularization that gradient descent is imposing, and what role does the infinitesimal regularization play in these interpolating situations? But great question. I think it is also really important. Okay, Arun has a question. With the advent of multitask and incremental learning, does learning theory extend to those as well? Right, that's a really good question. So there's been a lot of work on these sort of directions. So the multitask in the sense of learning a representation that gets used across a bunch of tasks. Whole lot of work on that since the 90s. postdoc at ANU that I guess almost overlapped with Wee Sun, started some of that work, you know, way
Baxter,
back.
right? Yeah.
Yeah, John Baxter, that's right. I guess you had moved on already. You graduated, yeah.
No, I met him in London with John Shaw Taylor. Yeah.
Of course, that's right. Yeah. So yeah, and he came to ANU from London. That's right. So there's been a lot of work in that direction. I mean, I think some of these there are a few different directions that, you know, there's been some really interesting work, but there's still a lot open. You know, one of them is understanding representation learning and how you can come up with good representations in some sense along the way, you know, the way that ImageNet is used for all sorts of other applications. I think that's really fascinating. You mentioned incremental learning. I guess there are these you know, approaches to doing one-shot or few-shot learning, you know, that are also you know, have attracted a lot of interest. You know, I think there's a lot that's open there that I think is really interesting. So yeah, great question, Arun. I definitely think there are you know, exciting avenues in those directions too. All right.
Okay, I think there are no more questions. So maybe
all exhausted.
Last question, like, what's the exciting direction? So is benign overfitting the exciting direction that
I think it's pretty fascinating. Yeah.
Okay. So it's,
you know,
it's trying to answer the question that I guess every so often comes up, that why does deep neural network generalize so well? Is that what it's essentially trying to answer?
I think it's a phenomenon. Right. I think that's right. That is a pressing question. You know, I think the other one is, you know, once the big motivating question there is, you know, can we design things that are better? Right. So these methods empirically seem to require a huge level of over-parameterization, right? You have way more parameters than the sample size. You know, the conjecture is that this is helpful from a computational perspective, that it doesn't hurt from the statistical perspective. But you know, can we do something better? If you think in terms of the energy that's required to train these things, if the sample size, you know, is your complexity parameter, and you're then introducing a number of parameters that exceeds that, then, you know, going through one round of gradient descent is quadratic in the sample size. This is outrageous, right? So can we do something that's more efficient than that, but has all of the same approximation, you know, statistical and computational kinds of advantage, or maybe even a computational advantage over those approaches. And you know, I think to understand what's really behind those methods, we have to understand the things that are sort of shocking about them, right? And I think this is one of those really surprising. So the other thing I think that's surprising is the how effectively these very simple-minded optimization methods can lead to very good empirical risk. You know, when it's a difficult non-convex optimization problem that they're solving. And you know, it seems to be that happens once you sufficiently over-parameterize things, and then, okay, then you get this benign overfitting question as the pressing one, right? I mean, I don't think we completely understand that computational question, but even so, assuming that's what's behind it, you know, why is it reasonable to have these overfit, complex overfit models? So yeah, I mean, I think that's really fascinating and kind of exciting new direction, right?
Yep. Sounds like there's sort of great things for the students to work on, right? Those who are interested.
That's right. Yeah.
Yeah. Yeah. Okay. I think we are slightly over time. So with that, let's thank Peter for the fascinating talk. Yeah. Thank you. So
Thanks very much.